Yukawa Institute, and he will give a talk mostly on a kind of uh, scalar tensor theory, which may be DHOST or U-DHOST and minimal modified gravity theory. Antonio, are you ready?
Yes, I am. I'm trying to. Can you hear me?
Yeah, I hear you.
I'm trying to share my the slides from my tablet, but I don't know. Maybe I cannot. Okay, forget about. I'm gonna use standard procedure. Okay, let me try to do it. Wait a sec. You should see now this, and let me actually go like. You're not seeing anything, right?
Not no, I didn't see anything. Okay. Okay, I see already.
Okay.
Okay. If you're ready, you can start.
Okay. So first of all, I want to thank the organizers, in particular Campi, who invited me to give these lectures. I'm sorry, I really wanted you. I mean, you should know me that I like so much Thailand that I try anytime to come to visit Thailand, but somehow, because I had to take some medical exams, I prefer to remain in Japan this time. And I was asked to give some lectures on modified gravity, in particular theories with higher derivatives, which have constraints. So I'm going to start today with that. Okay, so first of all, let's start with the motivation, why we care about it. I'm going to talk about the Strugatsky theorem, maybe first Pauli action a little bit. The degeneracy removes the extra pair of modes. I'm going to talk about Ondesky gravity in Galileons a little bit. I'm going to introduce the ADM toolkit and phase space counting, in particular those theories, diagnostic protocols, and exercises. The exercise for the students, please, I suggest you to do it. And in case you don't know the results, I can also share my own solutions. To motivate more the modifications of gravity, so I would say that the standard model cosmology lambda CDM has been remarkably successful. And it describes the temperature fluctuation, the cosmic microwave background, large-scale distribution of galaxies, expansion history of the universe. However, it relies on two mysterious, fully understood components. One is dark matter, and the other one is dark energy. Now, there is strong motivation to consider dark energy to be just a cosmological constant. However, from the theory side, we should be thinking about other possibilities in general, and maybe going back to cosmological constant if nothing else can work. And from the data point of view, of course, one has to check whether this simple, extremely simple cosmological constant model fits completely the data or not. In particular, the cosmological constant lambda drives the late time accelerated expansion of the universe, which is good. But it suffers from theoretical issues. I would say fine-tuning problem, discrepancy of the 120 order of magnitude between predicted quantum vacuum energy and observed value. Although the same fine-tuning problem can be applied to other theories unless they have some method to control the quantum vacuum energy. And then the coincidence problem, why are the energy density of matter and dark energy comparable exactly today? Again, this is a problem that can be shared by several other models. But then why modify general relativity? Modifying gravity on cosmological scales offers an alternative to dark energy for explaining cosmic acceleration. General relativity describes gravity uniquely as an interacting massless spin-2 field in 4 dimensions, whereas modifying gravity typically introduces new degrees of freedom, although constraining the minimally modified theories, as we will see in the last 2 lectures, provide important counterexamples. And the simplest extension is an addition of a scalar field leading to scalar tensor theories. Okay, so let me describe a bit linearized gravity in GR. Before studying modified gravity, let's explicitly count degrees of freedom in GR. We can do it in several ways. Let me introduce one here. Consider small metric perturbation H A mu around a flat Minkowski background, eta mu. So we can split the G mu into an eta mu plus H mu. And H mu is much less than 1. Okay, so this is an expansion around Minkowski if you want. The inverse metric to linear order is given by this relation. Indices are raised and lowered with eta mu. And when we expand the Einstein-Hilbert action to quadratic order in H mu, here's a fierce Pauli action for a massless spin-2 field. So we don't have any massive term because we just set the mass to be 0. But we get this object here, which is quadratic in our perturbations. And yes, here H is the trace of H mu. So when we take the action and vary with respect to H mu to find the equations of motion for the field H mu, we have this relation here. This is for the students. You can verify step by step, and if you find something, please let me know. By the way, I have also lecture notes available. The lecture notes are not exactly the same as the slides, but they are more involved. They go more into details in general. So if you don't find some calculation here, you will find it there. And if you still do not understand something, you can ask me. So after integrating by parts and discarding the boundary term, we're going to come back to that actually. But we get the equation of motion, and given in this form, the term in brackets is proportional to the linearized Einstein tensor. Okay. So in other words, if I take the Einstein tensor and linearize, I get up to a numerical factor exactly the same object here. So of course, setting to 0, we get the vacuum linearized Einstein equation. We have diffeomorphism invariance in general relativity. And for theories which do not in general introduce external fields and or prefer frames. In any case, in this case, we do have linearized diffeomorphism. So H mu has 10 independent components, and we have gauge symmetry, which eliminates 4 components, essentially, if you want, for choice of the coordinates. And then we have equations of motion. The 0 mu equation contain no second time derivatives of the dynamical spatial metric, and they act as 4 constraints. So we have 10 minus 4 gauge minus 4 constraints. We have 2 propagating degrees of freedom. Now, okay, this was very initial, not so simple, but nice exercise calculation. Let's go into what I would call the Ostrogradski's theorem. Any non-degenerate Lagrangian, depending on second or higher order derivatives of the fields, will lead to an unbounded Hamiltonian, causing a ghost instability. Okay, the Lagrangian must be non-degenerate on the second or higher order derivatives of the fields. And an unbounded Hamiltonian means that energy can be as, let's say, as negative as possible. And therefore, this would cause ghost instabilities because the presence of a ghost means that the system can decay into lower and lower energy states, radiating infinite positive energy. What it means is that if I have, for some particles with positive energies, but if I have a spectrum with negative energy,
Sorry,
yes.
Antonio.
Yeah.
They have questions.
Oh, please.
About this theorem, I have a question. Recently, a paper appeared on arXiv about the ghost. I think by Neil Torok. They say ghost it's not anymore problem for higher curvature theory. It's related to the normal state. It's not related to the energy of particle. What do you think about that?
Okay, I didn't hear properly. Can someone?
That's one doesn't work much. Can you go down and use this microphone? Sorry.
Can you hear me?
Yes, now very well.
About Ostra Gradiski theorem about the ghosts in higher derivative theories. Recently, it has been paper by Neil Turok, and he said in that paper, ghost does not relate to the energy of particles in higher curvature. It depends. It relates to the norm of states in the Hilbert space, but in Hilbert space, since the norm of the states always should be positive, therefore he goes to the crane space. In crane space, since it has a causal structure, norm of states can be negative, and this is why they say. There is not any more problem with the ghost in higher curvature.
Yeah. Okay. Thank you very much
Yeah.
for the night. Okay. Let me put this way. There are ghosts may not be a problem. I would call it this way. There are indeed ways to take care of the ghosts. In particular, I know an approach which is called Fakeon approach. And essentially what it means is that it's a way to, but they had to change, in general, quantum physics has to be adjusted so that it can consider presence of ghost particles. After doing that, yes, theories may not suffer from problems, true. But here, I just say that this could be potentially a problem because adjusting quantum gravity doesn't mean necessarily that, okay, finding a, how can I say, a prescription to cure the ghost doesn't necessarily mean that nature follows that prescription. Okay, so, right. So let me go into, so I just want to prove classically that the Hamiltonian may become unbounded from below, actually. So let's consider a Lagrangian, which is a function of Q dot, and Q double dot. And I'm going to consider a non-degenerate Lagrangian, which means something that I'm going to tell you in a second. So let me build up the action. Notice this is just an example of a field Q which leaves only one dimension, time. So varying the action yields this kind of expansion in delta Q dot, and delta Q double dot. We can rewrite the following into this form, namely the equations of motion, which reduce to this object here, and this should be set to be 0. And then we have this boundary terms, which I call it P1 delta Q and P2 delta Q dot. This is just by when we do integration by parts, we will get this object here. And then it's convenient to rewrite delta Q as delta Q1 and delta Q dot as delta Q2. So you see that the boundary terms, it comes in the form of P delta Q, P delta Q. Okay, where P is this object here. When we do integration by parts, you will see that this term in delta Q has 2 terms, whereas this P2 is just this. In the standard case, this would be 0, and this also would be 0. Yeah. Now, in general, this object here is going to be a function of Q1, Q2, because Q2 is equal to Q dot and Q double dot. So we assume that the Lagrangian would be non-degenerate. So which means that this quantity is different from 0. And then what it means from this relation here is that I can solve that relation in general for Q double dot in terms of Q1, Q2, and P2. Then the Hamiltonian via Legendre transformation is P1 Q1 dot plus P2 Q2 dot minus L. And now Q1 dot is just Q2, and Q dot is Q double dot, which can be rewritten in terms of this form. And we have now the Lagrange, the Hamiltonian in terms of our phase space variables. Notice that I introduce in this way, but we'll see later on that another way to introduce, in a more standard way to introduce the canonical momenta. But in any case, if you trust this, you will see that no matter what this is, and no matter what this is, we have a term here, which is P1, Q2. And notice P1 doesn't appear anywhere else. So therefore, this quantity here actually, because P1 in principle can go from minus infinity to infinity, makes, no matter what is the sign of Q2, H unbounded from below. Okay, this was, okay, let's give a concrete fourth order oscillator example. So let me give this, this Lagrangian here. And as we'll see, we have epsilon. Epsilon we assume to be different from 0 in general. It's a very simple Lagrangian with higher derivative theories, which is non-degenerate. So the equation of motion is fourth order. So what it means, we have to set 4 initial conditions. The momenta, as discussed before, we can define P2 to be epsilon Q double dot and P1 Q dot minus epsilon Q triple dot. And the Hamiltonian becomes this object here. Now, again, there is this linear term, which makes H not bounded from below. You may say, there is also this term here, true. This is always negative. But this is just because we picked up a plus sign here. If we would put a negative sign here, this would be positive, actually. So notice that in this case, of course, this would be not solving the fact that H is unbounded from below. So to avoid the, so in other words, flipping the sign here does not avoid this presence of Hamiltonian being unbounded from below. The Scoragasi theorem assumes the highest derivative Hessian is non-singular, so therefore we can propose, I was not the proposer of those, but okay, in these lectures, okay, we propose the key idea. We can build healthy theories by violating that assumption in a controlled way. If the system is degenerate, constraints appear that can remove the extra ghost canonical pair. Okay, so what follows is probably one of the most important calculations we're going to do in the whole lectures, okay? It's simple, but very, I think, hopefully, illuminating. So let's examine a mechanical model which mimic those theories, okay? And this example should be used as much as possible. Probably I will not use it as much as I would like to, but it's really useful. Okay, so we have this Lagrangian here. We have phi double dot square, phi dot, q dot, phi, and the function of phi and q. So we have two fields, phi and q, and for the field phi, we have a non-degenerate Hessian for the second derivatives. So this should, in general, allow for the existence of the Osogasky's ghost. But we will see that DHOST acts in a way so that the ghost actually, through constraints, okay, is removed. So let's replace phi by q and then force it with the Lagrangian multiplier. So we write it in this way. Now, what we have done here, we introduce a field, a Lagrangian multiplier lambda, which is still a field. We introduce a field, actually. And this field sets a constraint, q is equal to phi dot. Now, let's stop for a second here. And this is an important example because it already shows these Lagrangian multipliers. You notice the Lagrangian multipliers sets q to be phi dot. Q to be phi dot can be seen in two ways. In terms of phi, it's a differential equation. But in terms of q, it's an algebraic equation. Q is equal to phi dot. So there are no initial conditions associated to q. Q is always phi dot, no matter what. Whereas phi dot is equal to q, I cannot say phi is equal. In principle, I should do the integral plus some initial condition. But in terms of q, because it's algebraic, I can actually I can replace any algebraic equation for fields. So if I replace q to be phi dot, of course, this object goes to 0, and we will go back to this Lagrangian here. Okay. Naively, that says that this Lagrangian is actually equivalent. Naively. But strictly speaking, mathematically, I would call to Lagrangian equivalent if they lead to the same equations of motion. Of course, this will have an equation of motion for q and an equation of motion for phi, which sets what is lambda, and combining them, we should get equations which are equivalent to this. Okay. Now, let's consider now, because we wrote now this sector here in terms of standard first derivatives. So let's collect the kinetic object. This is linear. For me, it does not belong to a kinetic matrix. But let's consider the quadratic terms. And the quadratic terms are can be written in terms of the kinetic matrix M, A, B, B, C, and with determinant AC minus B squared. So if I have this Lagrangian here, if I take variation with respect to big Q and little q, I get my equations of motion, A, B, B, C, Q double dot, little q double dot is equal to this object here. I do have other two equations, which I didn't write here. One equation is the equation of motion for phi, and the other equation is the equation of motion for lambda. But if the determinant of this matrix is different from 0, we can invert this relation here. So both acceleration q double dot and little q double dot are fully determined. And then we had to set up initial data for q, q dot, little q dot, phi, and lambda. And the reason for this is that the equation for lambda is phi dot equal to q, which means that we had to provide an initial condition for phi. An equation for motion for lambda, you will see, for phi, by integrating by parts, it will give you lambda dot. So that equation also, to solve it, we need to give one initial condition for lambda. Okay. Now, and therefore, what we are going to see, we're going to have a 6 initial condition, 4 plus 2. In the original Lagrangian, we will say 4 because we had phi double dot square, and then 2 because we had the other Q field. So 6 initial conditions remain. Of course, the two Lagrangian are equivalent. And therefore, we would say that I had 3 degrees of freedom, and one of them is the unwanted higher derivative of Stokes-Graskin's mole. Now, let's assume in the example before that C is different from 0, but we have a degeneracy condition only. So we have a constraint. Okay. In general, it doesn't hold, but we suppose that there is this constraint on this parameter. AC is equal to B squared. So what happens in this case is the rows of M are linearly dependent. Multiplying the second row of equation of motion by B over C, and subtracting from the first cancels the accelerations. We are left with an algebraic relation. And this is the Lagrangian form of the secondary constraints. The primary one is psi 1 is equal to PQ minus B over C, PQ equal to 0 on the surface constraints. What does it mean, the whole thing here? It means yeah, so if I combine, okay, so let me go into this. All right. Now suppose that C is different from 0, okay? I can solve this equation for Q double dot. Q double dot is going to be equal to something divided by C. I replace into the other equation, and because of the degeneracy condition, I actually get this relation. And this relation is a constraint, because this sets constraints on the fields, or if you want, on the initial condition. Now the initial condition, not 6 anymore, but I get this other condition here. But this condition here actually comes in the Hamiltonian formalism as a secondary constraint. And the primary constraint is given by this. How do I see this relation here? The way to see it is when we define the momenta. This is written in this form. This is a Lagrangian for standard. So we know how to define P capital Q. So P capital Q will be dl over dq dot. Okay? And then we will have A Q dot plus B little q dot. And then the momentum associated to little q, P little q, is dl over d little q dot, which means B q dot plus C q dot, little q dot. Again, because C I assume to be different from 0, I can solve what is q dot in terms of P little q dot, replace into the other equation for P q dot, and what we will find is this quantity actually is 0. All right. because this will be in general proportional to the determinant of the matrix, the kinetic matrix. But because it vanishes, this quantity becomes 0. So what it means that I have a constraint here. And if I take the time derivative of this constraint, which means I had to do the Poisson bracket with this constraint psi1 with the Hamiltonian, I will get these secondary constraints. And what it means that I have now 2 extra constraints, and with 2 extra constraints, which before I didn't have, I can remove 1 degree of freedom. So I should expect that the system, when this object holds, not to have 3 degrees of freedom, but 2. Is it possible to see it in a different way? For instance, in a Lagrangian form? And yes, right. So right. So let's define this x to be q plus b over c phi dot, which is essentially q plus b over c big Q. So how did I get this relation here? Essentially, this is a theory definition for little q. So little q is x negative b over c times capital Q. And so you notice that you have this 1 and then negative b over c. Yes.
Sorry, Antonio. Can you repeat again how can you find x in such relations?
Yes.
I think it's quite important how to get this form of x, for example.
Yeah, but let me put it this way. If you had this matrix, if you put 1 and minus b over c, you multiply this matrix by 1 and minus b over c, this term becomes, the second term becomes b times 1 plus c minus b over c, so this becomes 0. And when you multiply the first row by 1 and minus b over c, you will get a minus b squared over c, and this quantity also will be 0. So 1 minus b over c is actually the eigenvector with 0 eigenvalue. And essentially, Q follows this. We have a variable minus b over c.
Okay.
Essentially, here the transformation is suggested by the eigenvector. Okay, now having said that, actually, well, you will see that indeed one equation of motion is simply, so if I go into this form here, the second one, now I have this q double dot, but I will have this, you see, I have here a linear combination of capital Q double dot and the little q double dot. If I replace this relation here, I will get Cx double dot plus Vq equal to 0. And you notice this is V dV over dQ, where Q is defined as X minus B over C phi dot. So the equation becomes a second order differential equation, where the highest derivative is in x double dot, and V contains phi dot. The other equation, the other equation comes from this, and the equation motion for phi. So phi will have yes. So we had that lambda was equal to, this is phi dot plus b over c b comma q. But we had the other equation, which is the equation motion for phi, which says that lambda dot is equal to minus v comma phi. Now lambda dot is given by lambda is given by this, okay, sorry, by this relation, and I had to take the derivative. After doing that, you will get this equation here. And this equation here becomes an equation for phi double dot. There is x dot here, and v is a function of phi and q, but q is x minus b over c phi dot. So this is a second order differential equation. If this quantity is different from 0. If this quantity is exactly 0, your system reduces, becomes a bit weird. This is going to be not DHOST, but constrained DHOST, okay? And therefore, the number of initial conditions will change. But if this is not 0, what we have is a closed system for phi and x, where we need to impose only in total 4 initial conditions instead of 6. Okay, so the crucial point essentially is to find the constraint which sets the determinant to be 0 and the eigenvalues, the eigenvectors. Okay, to avoid the Ostrogradski ghost, one can construct a theories whose equation of motion remains strictly second order, despite the higher derivative terms in the action. The most general scalar tensor theory with this property is on density gravity. A paradigmatic building block is the Galilean term. Oops, I went back. So let's discuss for a second the cubic Galilean. So this object here has x box phi, where x is this object here. Let's vary this action with respect to phi only, okay? I don't consider taking variation of the metric because it's going to be simpler, that variation. But the equation, the variation with respect to phi is interesting. So I take a variation with respect to x, leave the box phi unchanged, and x times the variation of box. So taking the variation for x like this, and the variation of box phi to be this, assuming that I only take a variation with respect to phi, then I have that the variation for x, for the action is this. Okay, so we should integrate by parts, and we get this object here. This object has 3 derivatives when I do d mu of the box, and I have box x. So the first terms yields this object here, which has this object here plus this box phi squared. So that we have a dangerous term, this cubic derivative. Now, the second term, so if I take the box of x, that will give you na bla nu of dx dx. So once you expand, you will have these two terms. Now, the first term is actually yeah, so this is nabla nu on phi, and this is nabla nu on phi. Now, the derivative, you can flip them for a scalar. So this is just this quantity here, nabla nu phi squared, actually. So this doesn't have three derivatives. Now, if I write this object here, if I want to have a box, I have to flip these two derivatives. And flipping these two derivatives, I get this object here, so nabla nu of the box, minus a Ricci scalar. Now, this term has three derivatives, and it exactly cancels out the third derivatives coming from the first term. So in the end, the equations of motion become second order. Box phi squared minus this term here and this term there. You notice that it's second order, but the second order are not linear, okay? But still, it's a second order term. And this essentially removes this potentially dangerous terms with the third derivatives. I'm going to go through, I have 15 minutes for the first class. I should be able to finish, hopefully. So Fourier space-time by space-like hypersurfaces sigma t. The metric is split into lapse, shift, and induced metric hij in this way. In this form, the extrinsic curvature is given by this relation here. We are going to see in a second, but a bit more, but not much more than that. But for me, what is important is the time derivative of the spatial metric is inside this Kij. So anytime we see Kij, we should think of one derivative term, if you want the proper time derivative term of the spatial metric. So if you use the Gauss-Godazzi relation, the Ricci scalar decomposes into this form here, where this is a purely derivative, spatial derivative of the metric, whereas this one will have kinetic terms, okay, because Kij has h dot ij inside, and this is a trace of k squared. Now, in Einstein, if I have only Einstein-Hilbert, the momentum πj is written in terms of kj, and actually you can invert kj in terms of πj. And the general formula for configuration space or degrees of freedom is 1/2 times the number of phase space variables minus 2 the number of first-class constraints, and minus S, where S is the number of second-class constraints. In GR, Hij, so I consider N and I as Lagrangian multipliers. So my variables are the spatial metric, which has three-dimensional symmetric matrix, so 6 components, and we'll have 12-dimensional phase space. The Miltonian tri-momentum constraints are all 4 first-class constraints, so I don't have second-class constraints. So number of degrees of freedom in GR is 1/2 12 minus 2 times 4, which is 2. Now, let's consider the possibility in DHOST, for instance, that I have a scalar field, And of course, I have the special metric. And I use the special metric in terms of ADM. And the fact that I have a scalar field allows me, and I had to consider phi to be time-like, allows me to make decomposition. I introduce this capital Q mu to be d mu phi. And A star to be A mu Q mu, and A mu hat to be H mu nu Q nu. We will see that N mu is related to this Q mu. It's just that N mu is orthonormal. So we can introduce this projection tensor, delta mu nu plus N mu N nu. And by using this relation here, H mu is given by these two terms here, we can write that Q mu coming from contraction of delta mu nu with Q mu. Q mu is equal to this, has this split here. So since n squared is equal to the negative 1 and n mu is orthogonal to n mu hat, we also have that x is going to be minus a star square plus ai. Yeah. The minus sign is the norm of the time-like normal. The cross term vanishes by projection. So we can use the fact that Q nu is the gradient of a scalar, and the fact that the anti-symmetric second derivative is 0 to eliminate the ai hat dot as an independent velocity. So keeping only the time derivatives in the full 3+1 decomposition gives that this object here, and I only restrict to the kinetic term, as an object which depends on a star dot and an object which has kij. One can expand this, neglecting the terms which don't have kinetic terms. And we will have this kind of object here. So essentially we'll have a tensor lambda mu nu, which multiplies a star dot, and another tensor which multiplies kij. And the reason I do that is because in kij, I have the time derivative. And in a star, I have the time derivative. So in other words, this is a way to keep track of derivatives. Yes. And this is a bit similar to the example that we saw before, where I have Q, big Q dot and little q dot. Okay. So I will essentially go back to that example. And indeed, what happens if I have a quadratic term in this delta Q, then we will have, in general, this form, an object which multiplies a star dot square plus 2 bij, a star dot kij, plus this other object here with 4 indices, which multiplies kk. And this one can be built, explicitly. And in the lecture notes, I think there is. Now, what happens here? Now, this is exactly a similar form, analogous form to the action that I was telling you as an example, where I had this matrix M multiply the derivative of the fields. We have something similar. And the elements of this matrix essentially are this A, Bij, and this. Okay, so something that this object here will shift doesn't change much, but for me it's important that one, of course, if you add kinetic terms, you will change this relation for A, Bij, and Kij, And that's exactly what we want to know at the end when we want to find a degenerate condition. So this is the field theory analog to the degenerate mechanical model, this one that I was telling you before. Now, the kinetic matrix is A, BKL, Bij, Kij, KL. So what we would like to find is non-zero eigenvectors for which if I multiply m times this is equal to 0. But what it means the determinant of this object must vanish. So testing for degeneracy, we will have the pair V0 and Bij is a kernel vector, not a new field, okay? That was like 1 minus B over C. It's not a new field, it's just a kernel vector. So, but that vector forming this form must satisfy this relation, okay? When applied to this M, I should get 0. So contracting the canonical momentum with the same pair cancels all velocities. Now, again, so what we would think, if I have this, I can find what are my canonical momenta by taking the variation, the variation of the action with respect to A star dot and Hij dot. So it will give me the Pij and the P star. And the fact that I have this relation, I will have a primary constraints on the P, which will then give me a secondary constraints and will kill the extra degrees of freedom. Now, DHOST requires this to be true on every foliation. U-DHOST, it's only true on the scalar foliation. I don't have much time. When analyze and modify gravity action, use this other protocol. Choose a foliation and list every variable carrying normal time derivative. Compute the Hessian before using background equations or fixing a gauge. Find the null vectors and translate them into primary constraints. That's what we have done in our little example and should be done in general. This is at least, I'm not an expert in those, but this is what I can say about the theory. Now, preserve primary constraints in time, okay? So what it means that we had to take time derivative of the primary constraints, they will give us the secondary constraints. And count the degrees of freedom using the number of degrees of freedom is 1/2, number of the phase variables minus 2, all the first class constraints, and minus all the second class constraints. Only then expand about freedom elements of work and test ghosts, gradients, and strong coupling limits. Evaluating the Hessian only on freedom elements of work may reveal accidental degeneracy, it's on coupling, not a healthy theory. Now, what it means is that the fact that I don't have an Ostrogradski's mode does not necessarily mean the theory is always will behave. It could be some theories for which, we may have extra problems, okay? Not necessarily, not coming from the Ostrogradski mode. Okay, using computer algebra for gravity, the constraint analysis can be heavily computational. A common practice using software like Maple or Mathematica is for the students. I suggest to use both. In this class, I gave you some Maple code, but Mathematica is also very helpful. So in practice with this one, you can construct complicated kinetic matrix either in a complete abstract way or on a particular background. For simplicity, I assumed some particular backgrounds, and but you will see that some code is already quite complicated. Symbolically, compute the determinant to find the degeneracy condition, compute Poisson brackets or constraints to find secondary constraints, implement the toy mechanical mode in Maple and verify the determinant of M vanishes. Okay. For the generated mechanical model, compute the Poisson bracket and the primary constraint. Right. So this one I will leave you as exercise. This is a second exercise repeat the GR counting while including n and I and therefore conjugate momenta. Okay? And I would give it a summary and that will conclude my first lecture. When gravity is motivated by cosmological puzzles but introduce dangerous degrees of freedom. Oscularity theorem forbids non-degenerate higher derivative theories due to ghost instabilities. Degeneracy, as seen on Densky and those theories, provides constraints that eliminate these ghosts. Counting requires a careful constraint analysis, primary, secondary, and first and second class.
Okay, thank you very much. So, any questions about this?
Can you elaborate, like in the slide, you written that like the accidental degeneracy means like we have strong coupling. I don't really understand like why, like yeah.
No. It's not a strong coupling. I mean, the theory. No. Oh, okay. Strong coupling and degeneracy are different things. I mean, degeneracy is a set of constraints. Okay?
Yeah.
The constraints are things which remove degrees of freedom.
Yeah.
Okay. A strong coupling issues means the following. I don't have constraints, so I would expect some degrees of freedom to appear, but somehow in the spectrum I have less.
I see. Okay.
Okay. The constraint work, I put constraints, setting the determinant that m equal to 0 is a constraint that I put by hand. Nobody tells me that the determinant of m must be 0.
Yeah.
I assume the theory so that the determinant is 0. Can I do that? Well, that's the choice of the theory.
So it's kind of like you try to match the number of degree of freedom, like to match, like to be whatever we want, like by imposing the constraint, right? And this strong coupling means that like the matching of like the constraint degree of freedom is not like what we want, something like that.
No, okay. The game of the number of degrees of freedom is up to us. You can put as many constraints as you like, and we will see that maybe in the last lectures. Okay. The point is that if you constrain much the system, then the system may not have solutions. Okay. But in any case, yeah, you can add as many constraints as you like, and the constraint will kill degrees of freedom. Okay. Now, the strong coupling is different. The strong coupling does not necessarily, the theory does not necessarily mean is bad. Suppose I have a theory which has 15 degrees of freedom, okay, and I have and I study my Schwarzschild background, and I find 15 degrees of freedom which propagate happily. Maybe the theory is complicated, but it's a theory with 15 degrees of freedom. You cannot say bad, or maybe it's ugly, or Occam's razor says maybe you don't need 15 degrees of freedom, but still it's a theory which may be okay. The problem comes, now you have a theory with 15 degrees of freedom. That's your theory. You may like it or not, but it is a theory with 15 degrees of freedom. Now you study Milan method of Metz-Work, and you find that your degrees of freedom reduced to 3. And you say, hold on a second, where are the other 12 degrees of freedom? Because the theory has 15 degrees of freedom. At that time, you should worry that you have strong coupling. But if you build up from the beginning with constraints, theory which have, 3 degrees of freedom, and you study on freedom and Metz-Work, you have 3 degrees of freedom, then you are fine. You don't have strong coupling.
I see. Yeah.
Okay.
Yeah. Okay. Thank you very much. Yeah.
and you go down to use microphones. Actually, in principle, you can stay around here. It's better for you to ask questions.
Okay. Thank you for the nice talk. My question is the foliation applicable for any space-time or just for some specific space-time foliation is up?
That's a very good question, and that I think is going to be one of the crucial points of the. Okay. What you need is a foliation. Okay. If you want, so yes, in any space-time. Okay. However, one has to be careful. For instance, time is time. So what that means, time is an object which is, because of the foliation, chosen to be time-like. So the foliation may break down if time cannot be time-like everywhere. For instance, in Schwarzschild coordinates, time stops to be time at Schwarzschild radius. Below that, time is space-like. Okay, so in our theories, what we will actually assume, and this is usually a bit it's a bit overestimated or underestimated, sorry, that we need a time-like scalar, usually. Okay, so, and time-like scalar means a very strong constraint, a very strong dynamical constraint, which means that a time-like scalar is time-like anywhere, anytime. If such a scalar would go not time-like, then your foliation breaks down and your theory construction breaks down. And you don't know what you are going to get afterwards. Okay, so what it means is that, yes, provided you have a time-like object, for instance, a scalar which is time-like anywhere, anytime, then yes, that foliation can always be done. But the theory will have a problem in general when the foliation breaks down, when the scalar field, for instance, is, is not anywhere time-like. And then the situation may be problematic for the theory in general. But okay, for instance, we know Schwarzschild, if you change coordinates, which means if you change foliation, if you change your time, you can go inside, the horizon. For instance, with KS coordinates. Okay, and what it means that you are changing time. In general, it's just you are changing your time variable. In these theories, this thing will not be necessarily simple, because what it means your field phi can enter up to, if your field must be time-like, may be consistent with the KS coordinates, but inconsistent with Schwarzschild coordinates. Okay, so.
Okay, thank you.
Yes. Okay. Thank you very much, Antonio. And then we thank Antonio again. And then we have about 10-minute 10-minute breaks because a little bit late, so that we can come back in about 11:05. It's okay for you, Antonio?
Yeah, that's fine.
11:05 minutes.
Yes.
Okay. Let's take a break. Okay, I think now is the time to begin after lecture from Antonio. Antonio, are you ready?
Yes.
Okay, see you now. And if you're ready, you can.
Yeah. So I want okay. So the chat doesn't work. Can I write something in the chat?
The chat doesn't work. Sorry. Okay, I will check it. If something doesn't work, so that I let. Yeah,
Don't
yeah.
worry. So I wanted to. Oh yeah, maybe I can do something else.
Ôi,ปิดยังไงแชทเนี่ยโอเค
ต้องโหลดใหม่ไหมครับหรือว่า
ไม่เป็นไรเดี๋ยวถ้าโหลดใหม่ก็
เครื่องนู้นนะผมได้อยู่ แต่ก็ยังไม่มีใครส่งอะไรมา
ไม่ส่งรายมามันก็ไม่ได้อยู่ในแชทนี้แล้วป่ะ
ก็ถ้า Facebook YouTube มันจะขึ้นมาตรงนี้ แต่เดี๋ยวผมเปิดให้
โอเคได้ครับ
Okay, wait a sec, Let me try to do something. Okay, let me see. Okay, I don't know if you can see this. Maybe not very well.
Okay, we can see. Oh, you have.
So this was no as subsequent answer to PTU
Question. Okay.
question. So this was the change of variables. Okay, and how do I find it? Okay, so phi dot was a capital Q, so it was like this. So B over C divided by this. So what does it mean? It means that the two variables are actually Q is equal to Q, and little q is equal to minus B over C over times capital Q plus X. So this is, okay, this is a vector, okay? 0, 1 means a vector, and Q is the two variables. And you notice this is exactly the vector which it's the eigenvector of the matrix. That's how you build up the Fourier definition. Does it make sense?
Okay. Yeah. I see. You determine from the eigenvector that make it 0, right? Yes.
So let me try. Okay, let me go back now to the slides. Now the slides. Can you see the slides? Okay, you can see the slides, I guess. Okay, can I start?
Yes, sure. Okay, we see your slide now.
All right. Let me talk a bit more about the DHOST theories. I'm going to give an introduction and motivation. At the end, the composition, the composing second derivatives, the quadratic covariant basis, building a kinetic matrix, this formal maps and phenomenology, cosmology, summary. Of course, in 1 hour, this is going to be a bit too much, but I'll try to do my best. Again, the idea is to go back to that little example as much as possible. Motivation beyond generativity. Generativity is highly successful, but leaves open questions: dark energy, cosmic acceleration. Modified gravity introduces additional degrees of freedom, typically a scalar field phi. So how to construct the most general scalar tensor theory without instabilities? A key guiding principle: avoiding the Ostrogarsky ghost. The Ondensky theorem was discovered in 1974 by Ondensky, the theory, and the most general scalar tensor theory with second-order equations of motion. Second-order equations of motion are a sufficient condition to avoid the Ostrogarsky instability. For a long time, it was thought to be the most general healthy theory. Higher derivative theories generally suffer from the Ostrogarsky ghost. Associated with an unbounded Hamiltonian from below, as we saw, it creates a fatal instability, negative kinetic energy, unless we take care of the ghost in a quantum proper way. And standard wisdom, equation of motion must not exceed second order. So beyond Ondensky, GLPV, Gleises, Langlois, Piazza, and Vernizzi realized that second-order equations of motion are sufficient but not necessary. We can have higher-order derivatives in the action, provided they form a degenerate kinetic matrix. The degeneracy introduces the constraints, okay? Constraints. We put the constraints in the theory that eliminate the extra ghost-like degrees of freedom, and leads to theories known as beyond Ondensky and eventually DHOST. So DHOST means they generate higher order scalar tensor theories. They generalize Ondensky and GLPV. Economical question: how many independent acceleration can the equations determine? By ensuring degeneracy, the theory propagates exactly one scalar and two tensor modes. Okay, so that's the final aim, to have a theory which only propagates one scalar and two tensor modes, so 3 degrees of freedom on any background, unless that background could be strongly bound, strongly coupled. At the end, the composition, fluctuating space-time. To understand the ghost elimination mathematically, we use the Arnold-Wittgenstein-Misner decomposition. Space-time is foliated into 3D spatial hypersurfaces, sigma t, parameterized by time t. So we have the metric decomposition. The S squared is equal to minus n squared dt squared plus hij. So there's a standard EDN decomposition, provided we have a time-like direction. N is the lapse function, and I is a shift vector, hij is a spatial metric. The unit normal vector to sigma t is mu is equal to minus n0, and n mu up will have 1 over n plus possibly a shift, minus ni. And this mu satisfies the condition which is of a time-like vector, and mu is equal to -1. The spatial metric can also be used as a projector. H mu is equal to G mu plus N mu nu. The Stensky curvature Kij that dictates how the 3D surfaces are embedded in 4D, defined as the Lie derivative of the spatial metric along N mu. So Kij is 1/2 ln, Hij, which is 1 over 2n, Hij minus dn, Ij minus dj and I. Yeah, so sometimes I will not be exactly consistent with myself, because already here I introduced Kij, and if you want, this is already projected on the 3D surface. So there are also covariant definitions of Kij. Contains the velocity of the special metric Hij. Using the Gauss-Kodazzi relation, the GR action R decomposes into R3 plus Kij minus K squared. Okay, so now we can see from here that no time derivatives of n or ni appear in the action. Okay? Because Kij only has time derivative of Hij. And at most a special derivative of ni, and n comes linear. Since n dot and ni dot are absent, their conjugate momenta vanish. Pn equal to 0 and pi equal to 0. These primary constraints lead to the Hamiltonian and momentum constraints. Crucial for GR, having only two propagating tensor modes. Second derivatives of a scalar field. But now let's consider that we have a scalar field out of which we want to build up these DHOST theories. And typically they involve second derivatives of the scalar, this quadratic DHOST. There, of course, you can go further. Of course, it's not so trivial, but let's consider these quadratic terms. So phi mu nu is equal to d mu d nu phi. And we define the kinetic term of the scalar x. Here we call it g mu nu phi nu, to be consistent with the standard literature in DHOST. The goal is to see how phi mu nu behaves in the ADM language. So we choose the unitary gauge right? Now, this is a very crucial point. This slide is very, very important, actually. We choose the unitary gauge. So we assume phi to be time-like. And therefore, in that gauge, phi can be set as a function of time. Actually, phi can be even set to be the time, okay? But for now, let's only consider phi as a function of time. We are assuming that this object is time-like. Hypersurface of constant phi coincide with the spatial foliation sigma t. With the convention that x g mu nu is negative, so what it means is this field is time-like anywhere, anytime, we can define a normal, which is m mu, which is negative, the gradient of phi, divided by the square root of minus x. So x is going to be equal to, in this, because phi is purely time dependent, can be written as minus phi dot square divided by n square. N is the lapse, but phi dot is purely function of time. So, in principle, this object can be used to rewrite delta mu. So x is going to be equal to square root of minus x is going to be equal, if phi dot is positive, to phi dot over n. And therefore, we can write delta mu phi in terms of n mu and phi dot over n. So we expand phi mu nu. So phi mu nu is going to be equal to the d mu of our d mu phi, which we wrote as minus square root of negative x and mu. And then I can write this d mu expand. I will have a term which is minus n nu times d mu of the square root of minus x, and minus square root of minus x d mu of n mu. Now, in general, if we use n mu, then we can write the extrinsic curvature by writing that d mu n nu is equal to k mu nu minus n mu a nu, where A mu is the acceleration. Now, in principle, we should prove this one, but it's not so complicated, and possibly, yeah, this is a good exercise for ADM. Now, it's all right. We can actually show that phi ij is equal to minus phi dot over n kij. And n mu and nu, phi mu, it's this quantity where this dt is the normal time derivative. Or if you want, yeah, I mean, typically this will introduce time derivative of this object. But so what should be said here is that, so essentially phi ij is the projection of phi mu nu on the hypersurface. So we'll have hi mu, hj nu, which multiplies d mu d nu phi, and this will give us this quantity here. As you notice, this is proportional to phi dot and hij dot. Here, but you notice n does not appear with derivatives. But if I take the normal component of phi mu nu, you notice I will have, in general, this derivative, which also contains n dot. So n dot explicitly appears in components of phi mu nu. And typically, this is not so good because it will free up n as an extra field. Oops, sorry. So then Lagrangians with the phi mu nu, or box phi square will in general produce n dot square and n dot hij dot. So what it means that n will belong to the kinetic matrix. For a generic linear combination, pi n dl over dn dot is non-zero and independent. This would activate an additional higher derivative scalar mode. DHOST avoids it when the full kinetic block is degenerate. Now, the most general action at most quadratic in phi mu nu, it's p plus q box phi plus f phi. Q is just a general function of phi and x as well as p. This phi f function times the for each scalar, and then we have this linear combination of phi different operators, Li, acting on phi. And Ai are functions of phi and x. So f and Ai dictate the highest derivative terms, the kinetic matrix. We can perform 5 independent quadratic invariants from phi mu nu. I wrote it here, phi mu nu, box phi squared, and combination, which involve also first derivative, but it's always quadratic in this phi mu nu. Box phi, of course, is a contraction with g mu nu. Okay. Ondensky is recovered for specific parameter choices, A3, A4, A5 equal to 0, A1 minus A is equal to negative A2, and F is equal to that, actually. Substituting this relation, the class 1 or formulas gives A4 is equal to phi equal to 0. This is a useful symbolic check, okay? So when you want to check whether your results on those make sense, you use subset to understand whether this your equations go back to the standard Ondensky case. Quartic beyond Ondensky, GLPV, corresponds to. Okay, we have GLPV, also can be rewritten in terms of at least one part of GLPV can be rewritten in terms of this DHOST. We have F is equal to G4, A1 is equal to negative A2, A3 is equal to negative A4, and A5 is equal to 0. Not only that, but these two relations must be related by this F4 formula. Okay, having said that this general construction has a subset on Densky and fourth GLPV, let's define on arbitrary foliation A star to be n mu d mu phi. If we use a unitary gauge, this object will only have n0 up, of course, multiplied by phi dot. So n star will have phi dot. This was the variable capital Q in our first example. Remember, in our first example, we had a fourth-order differential equation. So we replaced phi dot with capital Q. And now we are doing the same because n mu d mu is selecting the phi dot term, and we call it A star. So A star corresponds to that capital Q. So the kinetic part takes the form in general, okay, expanding A1, A2, A3, 4, 5 into this structure here that we already saw in the last lecture, so it should not be a surprise. We have A star dot square plus 2 Bij, Ij, A star dot Kij, and then we have this object mat cal K, Ij, Kl, which multiplies two terms of the extrinsic curvature. Again, this is dot squared, dot, dot, and dot, dot, okay, for the Hij. Now, when we call it actually dot, we can actually give it a covariant meaning by multiplying the gradient. A star is just a scalar. So we can take the gradient of A star and multiply by T mu, where T mu it's nothing but in this coordinate 1, 0, 0, 0, 0. Okay. Okay, in unitary gauge, it contains n dot. This is useful intuition, but covariant degeneracy must hold before choosing that foliation. To remove the extra mode, this kinetic matrix must have a null vector. Okay, again, we are looking for the eigenvector with 0 eigenvalue. And the eigenvector must be non-trivial. Oops. Okay. Now, why the null tensor has only two coefficients? Okay, now the special coefficient contains only Hij and the preferred vector Ai, A hat I. Okay, so now what we want to know is this how to construct this Bij and this mat-cal. And also this object here will be Vij will be part of the eigenvector. And the reason here is that we want the theory to be a theory of the special part for which I have dot derivatives, and also the scalar. And essentially, given a scalar, I have a preferred direction vector, which is A hat I. In general, okay? Because I have these two elements, phi, and of course I could introduce other object, but then would make the analysis multi-field. I try to be only using objects with the 3D metric and the scalar field, and the scalar field produces intrinsically a vector direction, which is a hat I. Remember, the a hat I was the projection of the mu phi on the surface. Okay, so in general, then we can write Vij with two indices as a linear combination of Hij plus V2 AI Aj. And Bij will be similarly written into this form. I'm looking for these answers if you want. In a frame with AI perpendicular to Z, so if I go to an inertial frame, I can fix Hij to be diagonal, and if AI is along Z, we'll change only the last term. So this Vij will be V1, V1, V1 plus V2 A hat squared. Okay. Then, if we define A hat squared to be S, and we go into the DHOST theory that's Lagrangian that we set from the beginning, I will have a 3 times 3 matrix, okay? Separating the scalar, Hij and AI Aj part of M kin D equal to 0 gives that object there. And yeah, remember Hij is a 3-dimensional matrix, okay? So we will have that object 3-dimensional M scal times V0, V1, V2. B1, B2 come from our definition of this Bij. But we also have this K1, K2, which are the coefficient of the allowed special tensor basis after including F times R, okay? So this quantity can be expanded because we started with an action. We can, in principle, write it down. In the lecture notes, I think I wrote down, if not all of them, some of them. A non-zero can exist if the determinant of M is 0. Now we can expand the determinant in terms of A times this sub-determinant and so forth and so on. So if we insert the explicit object Ba in Ka and use the fact that S is equal to X plus a dagger squared, because that's the standard decomposition of X, if you want, and collect in a star squared, we will have the determinant of the kinetic matrix is proportional to this quantity here. And this quantity selects the scalar part. Now, the covariant degeneracy must hold for every normal and mu. This is a requirement in DHOST. Hence, for every allowed A star, all 3 coefficients, D0, D1, and D2, are set to vanish. And notice this is interesting because I've written S in terms of X and A star squared. The elements D0, D1, and D2 are only function of phi X, which are covariant objects. So when I set them to 0, I set constraints on the theory, okay? Not like the student said, this is a strong coupling. No, this is among all possible theories, I'm gonna set constraints. You may ask, what if I go out of those constraints? If you go out of those constraints, your system will not be constrained anymore, and you will have extra degrees of freedom. If that's good or not, that's another issue. Okay. So choosing D0, D1, and D2 to be 0, it's a choice that we have done, we do at the beginning by hand by choosing a particular subclass of the theories that we introduced before. And that subclass is exactly what I call DHOST. So therefore, we need D0, D1, and D2 equal to 0. For instance, here the first coefficient gives D0 is equal to A1 plus A2, x times f, which multiplies that object there, which is an equation purely, although we have used ADM splitting, but this relation here is covariant. So we can now, for instance, if we impose D0 equal to 0, we have a multiple solution. Either we pick up A1 plus A2 equal to 0, and that's a class call 1 solution, or we can pick up this other possibility, keeping A1 plus A2 different from 0. So essentially, we don't have the solution has branches, okay? So in principle, those theories should be studied branch by branch. Maybe, okay, so a simple way to read, is it a simple way to read why D0 has to look like that? Well, D0 is the algebraic intercept of the determinant polynomial when we set A star equal to 0. A star, remember, was the derivative related to the first derivative of the field at fixed x. So when we write down the A term was the term which was proportional to A star square. That term when is A1 plus A2 divided by n squared, and Bij, when we substitute A star equal to 0, becomes equal to 0. And therefore, the determinant will be, because Bij equal to 0 becomes block diagonal, and the determinant is just A times the subdeterminant. So it's not so difficult to understand that D0 should have this form here. Okay, the second fact in the previous slide is that metric block determinant after the FFX terms are included. This is only a coefficient extraction device. A star equal to 0 is not unitary gauge, okay? Because a star actually is proportional to the time derivative of phi. It's just an extraction, it's just you know, simplification, kind of mathematical simplification to get the result. Okay, so we have this class 1 defining property A1 plus A2 equal to 0, and this one contains some density and GLPV. We have a class 2 F different from 0, A1 plus A2 different from 0, scalar tensor gradient conflict, and class 3 F equal to 0, no standard Einstein kinetic term. Okay, anyhow, so there are classes, which of course, each one may have a different phenomenology. Some are maybe better than others. Okay, so for instance, let's set this class class 1 solution. So let's set A2 is equal to negative A1. So this automatically set D0 equal to 0. If we solve D1 to be 0 together with D2, in general, this gives A4 and A5 in terms of F, A1, and A3. So the degeneracy, these two degeneracy conditions fix A4 and A5, and then we are left with three free functions. So a quadratic class 1 theory has three arbitrary functions, F, A1, and A3, plus lower derivative ones, okay, P and Q. P and Q were not in the game because they were just standard on density terms. So program the A4 relations and test distinguished points. This is in Maple practice, or if you want, when you do, when you study these theories with some Mathematica or Maple. If you then further substitute A1 to be 2fx and A3 equal to 0, you get Ondensky as a simple check if you want to make. The software automatically simplifies the numerators to yield A4 and A5 equal to 0. Substitute GLPV forms and verify that A4 is equal to -3 and A5 equal to 0. Anyhow, so this is just a suggestion. We are almost at the end of the lecture, okay? So we can introduce a field redefinition. Okay, that's also very, this one I didn't put too much stress on this one, but this is also very kind of interesting point. So we can make this formal transformation by this. We set G min u tilde to be a function C of phi and x, which multiplies G min u, plus another function D of phi and x of phi mu. It's a bit non-trivial result, which I will not give it here. The class 1A is closed under invertible disformal transformations. In the absence of matter, okay, by the way, so this disformal transformation, what is this? So it's a change of variables, going from old G min u to new G min u. So in principle, that object should be inverted, because we would like to know what is G min u in terms of G tilde min u, because then we have to replace this one in the original Lagrangian to go to the new Lagrangian. So the transformation must be invertible. Otherwise, the transformation is singular. This is true also with the standard conformal transformation. Conformal transformation is when D equal to 0 and the function C is just a function of phi. In the absence of matter, any class 1A action can be mapped to a Ondensky representative. Choosing a minimally coupled matter metric makes the frame physically relevant. Okay. Caution, singular maps can change degrees of freedom. Okay. So indeed, when the map becomes singular, we should not expect this, the theories to be equivalent. But when they are invertible, yes, they are equivalent. So what to do about the disformal maps? Disformal maps is purely a field definition. A field definition in some cases may simplify or may actually make things more complicated, depends on the field definition you do. It's when we study differential equation. When we study, for instance, a differential equation that I told you before, in that one, a convenient field definition was to redefine Q in terms of X and phi dot. Same thing here. It could be possible that the theory somehow simplifies by using the Disformal transformation. People used it to find, for instance, new theories starting from previous theories. Okay, the luminar subclass. I'm not, okay, so in the lecture notes, there is something related to, I wrote a bit more details in the lecture notes, but one can show that for these theories, the speed of the tensor modes in general is not equal to unity, but it's going to be this f divided by f minus x a1. Now, in general, the speed of propagation, the square speed of propagation, has to be positive. Otherwise, fast instability will grow. But there is a further constraint coming from the observation GW 1708-17, which is essentially yesterday. Okay, yesterday was the so 1708-17. It's 8 August. 17 of August of 2017, and GRB 1708-17A constrains CT to be very close to 1. And therefore, the theory is, for example, in this class, the theories become very much constrained because XA1 has to be very, very tiny. Requiring luminarity on arbitrary cosmological background without background-dependent tuning gives A1 equal to 0. And class 1 degeneracy test then gives also A2 equal to 0. But then in that case, so if I set A1 equal to 0, which is still a DHOST, class 1, the remaining relation become A4 and 5 are fixed as a function of the three functions capital F and A3. So the surviving action, if I impose that the speed of the tensor mode to be unity, has a free function PQ capital F and A3. I have some Maple code available, and this does some calculation on the background only. It does not perform the full covariant classification. Okay, so it's a subset of those, and plus only describes the background. But for U-DHOST, I put a much more complicated code. So, yeah, a powerful technique to study cosmology is the mini superspace. It's a very nice application, which I suggest students to do it for any theory you have at hand. In particular, what we do is we evaluate the action on Friedan and Metterman's work. Friedan's work has a free lapse function and a general scale factor A, and the scalar field, which is a function of time. Okay, so the scalar field must be homogeneous and isotropic, is only function of time, and the lapse and the scale factor are also a function of time. Now, if you write down those theory, you will find that the term phi double dot and A dot combine into a perfect square, like this. And as you notice here, you will have time derivative, second time derivative squared, but also time derivative of the lapse. But the fact that you have this, actually, it just shows that the fact that you have degeneracy. You have a degeneracy condition. And the fact that you have a square, you can use it to, for instance, to change variables. Instead of A, you take a combination of B, which is a new scale factor, if you want, times, in the lecture notes, I put A to be B times an exponential lambda, and lambda is a function of phi. So when you take the derivative, you will have possibility to remove this term here. But as soon as we see squares, usually means that there is a degeneracy condition. Of course, this is a degeneracy condition working at the background level. What we saw before, it was true on any background. Linear perturbation in unitary gauge can be captured by an effective field theory framework. A bit more on this one in the lecture notes, but not much because this is already would be a class by itself, effective field theories. But in any case, these doors introduce additional EFT parameters, alpha L, beta 1, beta 2, and beta 3. Also, I don't go too much into detail because U-DHOST, I will stay more on U-DHOST, which is, in a sense, very similar to DHOST. So yeah, studying more in detail one or the other doesn't change much things, except that U-DHOST has some extra ingredient which are shadowy modes, but we're going to talk about it next class. So in the DFT language, the class 1 degeneracy condition translated into alpha L equal to 0. There are this beta 2 minus 6 beta 1 square. In the lecture notes, you will see more into detail. But you have this 3 conditions to satisfy. And this eliminates the independent lapse perturbation modes. After you do that, in this EFT approach, the tensor mode will propagate into this where it will be massless. As you see, there is no mass term. And we have this m squared, which is a function of time in this approach, must be positive. Otherwise, we get Gauss degrees of freedom coming from the tensor modes. And 1 plus alpha t must be positive. But we have strong constraints on alpha t to be very close to 0. So the FT action can contain delta n dot, but the class 1 degeneracy relation makes lapse the velocity enter only in a constraint combination. The momentum constraint ties delta n to the curvature perturbation, and the propagating variable is zeta tilde is equal zeta minus beta 1 delta n. So this combination here will remove the kinetic term of delta n. Picking delta n again, no propagating. So it's a combination of fields, which is the physical variable to consider to propagate. So after eliminating auxiliary fields, only one scalar mode remains, of course, if we don't introduce matter action. Stability in the scalar modes will need us to impose 2 conditions. One is the square speed of propagation has to be positive, and one is the no-Gauss condition, m squared a zeta to be positive. Yes. Yeah, maybe. Okay, so let's go one moment back into this tensor action Lagrangian, which is already simple. And I impose m squared positive, but I should also maybe say that here I put the lapse to be unity, okay, in this calculation here. The lapse at the level of the background to be unity. Now, m squared also has units there, but say if I multiply and divide by mass Planck square, and then I redefine gamma ij, I insert gamma ij to be m Planck inside, so gamma ij becomes mass, of course, have a dimension of a mass, and the new gamma ij, and what we have is a coefficient which is m squared divided by mass Planck square. Now this quantity better not to be going too much to 0, because this would lead to strong coupling. So the strong coupling coming from the kinetic term going to 0 it's not evident in this quadratic action at all, because in principle, you can introduce a new field, gamma ij, to be qij divided by square root of m squared, because m squared is okay. And hello? Oh, okay. But the point is that when we do that, the kinetic term will be standard, but the higher order terms like gamma ij, for example, delta phi, that will be getting m squared in the denominator. And then unless the term in front of that cubic term vanishes when m squared goes to 0, you will have that the term becomes, going to infinity. And that's signals strong coupling limit. So when the stability requires m squared greater than 0, but I would say m squared should not go to 0. Okay, same thing for the scalar mode. Also, scalar mode cannot have strong coupling limit, so n squared a zeta should not go to 0. And c squared should be positive, and also c squared not going to 0. So there is another strong coupling possibility there, which is the following. Now, if c squared is
Questions. Sorry, Antonio, they have a question, sir.
yes, please.
Is there an upper bound for CS?
Okay.
For C squared?
Yes. Is there an upper bound for c squared? I will. Okay. In phenomenological point of view, no. Okay. It looks like you have modes which go faster than light and faster than photon, and that's true. But this does not necessarily mean that you have breaking of causality, because the space-time is not Minkowski. The space-time is a space-time where Minkowski invariance is explicitly broken. So the mode will be faster than the speed of light, but this does not necessarily imply a problem of causality. What some people say, though, and that in standard field theory, to have modes which propagate with the speed faster than light will, in general, not have a UV completion, which is which satisfies some assumptions. Now that's true, but on the other hand, we don't know what is the UV completion of this. In my personal point of view, we don't know very much what is the UV completion of these theories, because maybe very the UV completion may not, for instance, be.
But the mass dimension of the coupling of the your S2 was 0, and this means there is. Please go back to the previous slide. Yes, here the mass dimension of m square is 0.
Okay. Yeah, honestly, here, okay. I mean, gamma j for me is dimensionless, but yeah, you can, of course, you can put dimension to gamma. Yes.
And this is why I don't know why did you talk about the fixed point of the theories, because when mass dimension is 0, this means the theory is renormalizable and there is no fixed point.
Yeah, but this is not the theory. This is the theory truncated a quadratic order. Okay, so this is just a quadratic order that tends to behave like that, actually. This is not a full theory. But in any case, yes, so in any case, we don't know the completion of the full theory. So in terms of phenomenology, it's totally okay to consider this. This, of course, will introduce other things. But that is a phenomenology of low energy physics. What I wanted to say. Yes. Something that I want to add before closing. I'm going to take a couple of minutes. C squared going to 0. Okay, so I put C squared to be positive, but suppose C squared is very tiny, but positive. Is it a problem or not? And then eventually it is a problem, because indeed, if you study cubic order theories, then what happens is that this non-Gaussianities, which is which essentially measures the effect of cubic terms compared to quadratic terms in a consistent way should be always small. But if C squared going to 0, those terms actually becomes very large and overcome the quadratic order. So what it means is that this linear perturbation theory would break down if C squared is very close to 0. So that's also a bit tricky limit. Now, let me summarize. So quadratic DHOST theories give the general degenerate scalar tensor action at the most quadratic in phi mu. ADM decomposition reveals the problematic and dot term, neutralized by imposing the degeneracy condition. Class 1A contains Ondensk and GLPV and maps between them via disformal transformations. GW 170817 limits the parameter space to the luminal subclass, and the supplied Maple background worksheet is a partial algebraic check, not a substitute for the covariant constraint analysis. So thank you very much.
Any questions?
No, I cannot hear anything. No. Somebody is talking. Campi is talking. I cannot hear anything.
Ted, do you hear me?
Okay, now, yes, I can hear you. Yes.
Okay.
Not hear me. Okay, can you hear me? Okay. Sorry. KAJ can be defined from the arithmetic, and also there is the covariant definition like the K mu nu. My question is that are the independent element of KAJ and K mu the same?
Yeah.
It's
Yes.
same. So they are the constant. Right?
Okay. So what is K mu nu and what is Kij? Okay. So Kij would be just the So if you in unitary gauge they are the same, but if you want, Kij is a 3 times 3 object. K mu nu is a 4 times 4 object, and K mu nu Kij would be Hi mu Hj nu of K mu nu.
Okay.
You can think about that way, actually. Now, in unitary gauge, where if you use n mu as your gradient of the scalar, and phi is purely function of time, then in this slicing, K mu nu would actually have zeros, on and the only non-zero term would be the IJ subset.
Okay. Sorry, Antonio. Please explain again because there are a phone call. I lose my concentration. Sorry. Please,
No. Okay.
explain
So
again. Okay.
okay, yeah. So what I would call, okay, so you have K-Mu-Nu, which is related to Nabla, Mu, and Nu plus the term which depends on the acceleration. Then you apply twice the projector. And then once you apply twice the projector, H mu, the acceleration term goes away. And then what you are left is a term which only has Nabla, Mu, and Nu. And you can show actually that this term actually reduces to Kij completely when you choose this new object. We have zeros in the 0, term and 0i term. And only thing which doesn't go to 0 is the three-dimensional subset.
Yeah. So okay.
So it's essentially it's the projection Hi mu Hj nu of K-Mu.
So in this case, I actually wonder what is the meaning of the temporal component of K or mu nu. There are some special meaning or have no effect on the dynamics.
And they will be related to this acceleration.
To be acceleration.
It's related to the acceleration of the observer.
Okay.
So essentially, you have to project K-mu nu not with H-mu nu, but with maybe N-mu.
Project with a normal vector or something.
Yes.
Okay. Okay, thank you.
Any more questions? So if no more questions, please thank Antonio again. And we will come back in maybe one. In one is okay for you, Antonio. 1 p.m.
Okay.
1 p.m. We come back.
For me, it's fine. Is it fine for you, or is it too short for you to have lunch?
I think it's okay for us. Yeah.
Okay,
Yeah.
so let's meet at 1 p.m. Thai time.
Okay.
Thank you very much.
Anto, there are now David Mota is here with us. Did you say hi to each other a little bit?
Yeah, actually, he kindly came to
okay.
Yeah, it was very nice to see him again, and I hope we said that I hope we meet in person next time.
Okay. Let's take lunch outside. Thank you very much.
Bye.
Hello.
Hello.
Hello, Antonio. Do you hear me? This is Siratan. Yeah.
Ah,
Yeah. So yeah, I don't know that you will not come here. but yeah, I just joined the yeah. Yeah.
hello.
Hello. Yeah.
Yeah. Because actually, I hope we go. I hope we get the bilateral grant. Actually, I mean,
Let's see. So I heard that like some your health condition, right? That you cannot come here.
yeah. But
I
I'm
see.
fine. The point that I don't have symptoms, but I had to check. I have something in my chest, and I had to check
Oh, I
what
see. I
it
see.
is.
Yeah. When I was in Waseda, they scanned my liver and they said that they found two more. So
Oh,
clinic report me to the university. University called Yukawa. Studio called me to go to clinic again immediately.
okay.
Yeah. To do like a CT scan But after doing that, after doing that, there's no problem. So yeah, some of my friends said that maybe they just want our money. Yeah. Okay. Students, do not ready? Just a few. Yeah. Okay. That's it. You ready? Okay. That's it. Ready. Okay, Antonio. Okay. Yeah. Yeah, everyone. So welcome to the afternoon section. The lecture of Antonio. So yeah, please start. Yeah.
Okay. All right. And okay. So so we continue with the U-DHOST theories and the shadowing mode. And okay, I'll try to be closing 1 hour. Okay, this lecture. Okay, so I'm going to talk about especially covariant gravity and unitary gauge, U-DHOST theories and degeneracy, a solvable shadowing mode model, cosmological U-DHOST model, and maple implementation of U-DHOST. So in scalar tensor theories, the scalar field phi often has a time-like gradient. So unitary gauge, we can choose the time coordinate such that phi is function of time. In principle, we can even call it the time, okay, tau. But function of time can be done because we can do time reparameterizations. Any function of time is okay. The action can be built from geometric quantities of the 3D spatial hypersurfaces. And if a theory is designed to be degenerate only in the unitary gauge, it propagates 3 degrees of freedom. What happens if we perform a general coordinate transformation? Okay, we're going to a bit answer all this. So in a general gauge, phi acquires spatial dependence. So a naive analysis might suggest the kinetic matrix is no longer degenerate, seemingly reviving the Ostrogradsky ghost. Okay, so if the idea is that we get degeneracy having used the unitary gauge, then say, okay, let's unmake it. And then one may say, okay, but then the kinetic matrix is no longer degenerate, so maybe we have an Ostrogradsky ghost. So resolution for a regular time-like scalar foliation, the apparent high derivative mode carries no independent initial data. It is a shadowy response fixed by an elliptic equation and especially boundary condition. It is not a pure gauge artifact. It's a bit tricky kind of theory because the mode is there but not propagating. Not only that, but in general, although the mode is not propagating, it must be there is an equation that must be solved for it. And this equation typically is an elliptic equation. Now, elliptic equation, which means nabla square, this equation will not be present at the level of the background, for instance, in cosmology, but in other situations, other environments, it will be there. So U-DHOST theories are covariant representation of the spatially covariant construction. Okay, so let's talk about a little bit of this Tuchel trick, which is actually a very useful technique. So procedure covariantize a 3D spatially invariant action into fully 4D diffeomorphism invariant theory. So we will talk about a simple 3D action with extrinsic curvature Kij and 3D Ricci scalar R3. And we write down as follows. D for x, square root of h, n, alpha 1, Kij, plus alpha 2, k squared, plus alpha 3, r cubed. And the coefficient alpha I are functions which may depend on time. Now, evidently, this function, this action here breaks explicitly general for the covariance. And another thing that we can see is that there are no time derivatives of the lapse n. N dot is absent because Kij only has h dot inside. So to perform this kind of construction automatically removes any possible n dot appearance. In fact, the momentum conjugate to the lapse vanishes by n equal to 0 because dl over dn dot is equal to 0. So now, and this is a very interesting point actually, we have this action here, explicitly dependent on time. So let's introduce a scalar field, phi, as a function of x mu, and promote alpha I, function of time, to be alpha I as function of phi. This phi would correspond to what we call the Stuckelberg field. The unit normal to constant phi hypersurfaces is n mu, which is, we saw already last time, minus the gradient of phi divided by square root of minus x, and x being g mu d mu phi, d nu phi. This construction makes sense if phi is time-like. And the unitary, because it's time-like, anytime, anywhere, we can even choose t to be phi. In this case, n mu dx mu is going to be equal to minus n dt. But mostly n is equal to 1 divided by square root of minus x. Okay? So essentially phi dot here is 1. So we can calculate the trace k, which is g mu nu k mu nu. And k is going to be equal to the d mu and mu. And because we wrote down what is the gradient of phi in terms of m mu, we can rewrite this one in terms of box phi and n mu d mu x. So the trace k is directly linked to the box phi. Squaring k yields terms proportional to nabla phi square, which is equivalent to L2 operator in DHOST. Okay, so we had before k squared inside our Lagrangian, and k squared now becomes related to this box phi, and now we have this L2 operator. Similarly, k mu nu generates phi mu nu, the L1 operator. So we can still use the Gauss equation, Gauss-Quadrats equation. And by substituting this into the 3D action, we obtain a 4D scalar tensor theory. Because the original 3D action lacked n dot, the resulting 4D action satisfies U-degeneracy conditions by construction. So this simple method seems to be quite powerful to generate actions. U-DHOST theories can break standard on density relation while remaining viable. Class 1 DHOST may have alpha h different from 0, luminal modes, additional impulse t squared equal to 1. Now, especially covariant gravity allows operator like DIN. So DIN actually, it's an interesting operator because it doesn't introduce and dot terms. So strictly speaking, the momentum of, if I have in the Lagrangian a term which is DIN, the momentum associated with that would be still zero because there is no n dot in the Lagrangian. And this DIN can be written in terms of, in a covariant form using G mu and nu, of course, where n mu is our orthonormal vector generated by the gradient of phi. But still, this DIN will give some effect, actually. In particular, this may affect the Poisson equation. Of course, this must be shown, but in principle, those terms are not just gauge modes. Okay, so those theories are degenerate before choosing a gauge. U-DHOST theories are degenerate only after choosing the unitary gauge. On the unitary foliation, di of phi is equal to 0. So phi does not have any special gradient. What happens is that this hat AI, which is the projection of the special gradient, is 0. A star will be simplified dot over n, and x becomes just minus a star square, because AI is equal to 0. So what happens here is that, remember that we can construct this Vij, which was part of the eigenvector, with 0 eigenvalue, because AI is not there, so this object is now proportional only to the special metric. And also Bij, which was the non-diagonal part of the kinetic matrix, is going to be proportional to Hij. Because AI disappears, we have only this Hij. And Hij, when applied to Kij, will introduce the trace of the extrinsic curvature. So what happens is that the matrix, the scalar kernel test, becomes 2 times 2, one related to A star and the other one related to the trace of K. In a sense, it's simpler. So now, it's simply because in any case, even in DHOST, unitary gauge is so useful, is so simple, even in non-density theories. Okay, so evaluate the covariant derivative polynomial on A star, which is now simplest to the negative x. Now remember, before we had the d naught minus x1 times A star plus d2, sorry, plus d1 times A star plus d2 times A star squared. Now, the whole thing here becomes, because A star is just x, the whole construction becomes the whole, degeneracy condition becomes automatically covariant, even though we chose the unitary gauge to find it. So A star equal to 0 extract the coefficient d naught, but we don't need to do it in our case. It was useful maybe in DHOST. Unitary gauge instead sets hat AI to be 0, and has A star squared is equal to negative x, which is different from 0 for a non-trivial time-like scalar. Now, U-DHOST imposes this one linear combination. Instead, covariant DHOST imposes d naught, d1, and d2 separately equal to 0. Of course, then U-DHOST seems to be, because you have only one single constraint instead of 3, is more general. So if we require null direction only on the unitary foliation, gives this condition. The condition wrote before becomes this equation 8, which is slightly complicated, but okay, but it's a condition. And again, we may have branches to solve this degenerate condition. So every quadratic dose theory satisfies this degeneracy condition, because this is the linear combination of three which are both equal to 0. But the U-DHOST theory satisfies this, but not all three covariant dose conditions. After removing a totally U-degenerate block, the following frames reduce this equation to the one 2 times 2 determinant. Okay. So here I gave an example of a paper I done with Professor Mokoyama and Dr. Takahashi. And we gave a slightly different notation, but Cu is the proportional to the condition that we found before. CD1, CD2 being set to be 0 correspond to setting class 1 dose theories. I just show this one because I think it's an interesting paper. You may have a look into that. And also discusses a bit DHOST and U-DHOST. Okay. So what I want to show now, so let's see MU, denote the left-hand side minus the right-hand side of the full U degeneracy condition on the regular sector when everything is, when, for example, GT doesn't go to 0, one can show that this CMU is actually proportional to CU up to an X. So as long as X is different from 0, they have the same solution. But X different from 0, of course, because we assumed that we can use the unitary gauge. But unitary gauge assumed the field to be time-like, so X must be negative. Okay, so here hierarchy of condition, regular class 1 DHOST or genuine U-DHOST, Cu equal to 0, whereas CD1 and CD2 are different from 0. We can do, okay, so we can build up the action in a way which is also very interesting. This is not done by me, but I'm going to refer to the paper in the bibliography of the lecture notes. We can define an action whose entire kinetic sector vanishes in unitary gauge. So this is an interesting, because this object here, this Lagrangian 9, actually, after direct ADN decomposition on the unitary gauge, of course, we have that the matrix, the kinetic matrix vanishes. Of course, it's not identical equal to 0, special derivatives and lower time derivatives term remain. It's useful because adding it does not rotate the null vector on the unitary foliation. So you can add always this object here without changing the null vector of the unitary foliation. So therefore, we can write this linear combination of FR plus from AI from 1 to 5 of Li, and we can decompose this action into that completely U-degenerate theory, and with a new combination, instead of AI, capital AI, we write alpha I. And because the operator is the same, we can actually map also this U-degenerated theory can be mapped. So we have a mapping between capital I and alpha I as follows here. So because now this one doesn't need to be studied because it doesn't give contribution to the kinetic matrix, one can actually focus on the last term with the alpha I. And now what happens that now we have three terms, this B, S, and T, which will enter later on in the kinetic matrix. After removing the total U-degenerate curvature block, so we define this V star, which is this transverse time derivative, A dot star minus an I di A star over N. And then we take the traceless part of the extrinsic curvature, and we take the trace of the extrinsic curvature. Why we do that? For V star, it's just because it's a convenient variable to put everything together. One actually can show that all the terms combine into this V star variable. And K, and the fact that we split the Kij because we want to write down the contribution of the kinetic matrix coming only from tensor mode, essentially, and the contribution of the kinetic matrix coming from the, let's say, the scalar part. And then we have this kinetic term, which is part given by this extrinsic, the traceless part of the extrinsic curvature. Let me call it tensor part, although this is a non-perturbative solution here. And then we have that the remaining kinetic terms only have V star coupled with the trace of the extrinsic curvature. So the kinetic term then simplifies a lot in one part, which is purely the traceless part, and the other part, which takes two variables, V star and K, so we can form a 2 times 2 matrix. Indeed, we have this, the kinetic matrix for the scalar can be written in this 2 times 2 form, and this determinant is very simple to write down. We have this x times 3t squared minus 4bs. And so therefore, because x is negative, as I said, this determinant vanishes when 4bs is equal to 3t squared. And in principle, we can do, in a way, kind of similar to the construction that we did in the famous previous paper. Sorry, in the first lecture, we introduced this variable x. Now we know what is the eigenvector with eigenvalue 0, which is 1 minus t over 2 a star b times hij. And then we can construct this using this eigenvector. We can construct variables for which the kinetic term becomes a square. Okay, so then consider two-dimensional Minkowski space-time. Okay, so now the fact that we have this square, then we have this non-trivial eigenvector with 0 eigenvalue, automatically says that we have degeneracy. Therefore, we would find primary constraints on the momenta, and the time derivative of the primary constraint will lead to secondary constraint. And then we have the Astogaraski mode to be removed. So we want to give a simple model. Consider two-dimensional Minkowski space-time with signature negative plus, and we construct the toy model action. You know, we have L is equal to minus 1/2 x minus mu xl4 minus L5 with mu positive. And the second term, the part in mu, is totally U-degenerate. And the first term supplies one ordinary scalar mode. So let's assume then, let's choose the unitary gauge. But first, let's consider, okay, so we have this phi bar t, and then phi to be t plus some perturbations on this. So expanding the quadratic Lagrangian, we will have for this chi dot chi a term which is 1/2 chi dot square minus chi prime square plus mu chi dot prime square. So there we have no, we don't find the absence at linear order, this one. Of course, the action is quadratic. Notice the absence of x double dot, and in particular also x double dot square. And the special relation, if we introduce chi to be, a packet, wave packet, then we have that omega, it's k divided by square root of 1 plus 2 mu k squared. So what we find is we don't find no high k gradient instability for mu positive. So if you want, I can find my group velocity. But the group velocity, interesting, tends to 0 as k goes to infinity. Okay. And this could be potentially a problem as long as the mode is inside my FT regime. But, okay, let's consider now, so phi bar, not to be only time, but time plus alpha x with a modulus of alpha less than 1. After all, I still want phi bar to be time-like. Now, the gradient is time-like, but not aligned with t. The Lagrangian now contains chi double dot square, a mixed derivative. The Lagrangian becomes complicated, and the special relation becomes a quartic polynomial in omega. So we have, if we just change this profile into t plus alpha x, and of course this is nothing but a time redefinition, then the special relation becomes a quartic order. A quartic order, you may say, hold on a second. We have inconsistency because before we had second order, now we have fourth order. What's going on? Two real roots, and in general, quartic equation may have roots. But if we interpret all Fourier propagated modes with arbitrary initial amplitude, the theory appears unstable. However, this misses the boundary value nature of the problem. So let's go back into our model. Since alpha is less than 1 in modulus, we can apply a Lorentz boost to align coordinates with the scalar gradient. T tilde is t plus alpha x divided by square root 1 minus alpha square. And you understand that t plus alpha x is what we're considering as phi bar in this tilde background. So with this boost, essentially, my field becomes t tilde at the new time. Of course, this is boost, so also x changes. We have x tilde is equal to x plus alpha t square root 1 minus alpha square. The Lorentz boost exists because modulus alpha is less than 1. So the equation of motion becomes second order in physical time t tilde. Now, if we use then, we had a very complicated equation, but if we use this boost, the equation becomes much, much simpler, with a structure which is very interesting. And as you can see from this action, we have only two time derivatives, two t tilde time derivatives. But we have a non-trivial Laplacian in x tilde. So we can rewrite the system in a slightly different way. We introduce an auxiliary field psi, and we define this kappa to be that number there. It's just a number, mu is positive, and alpha, modulus alpha is less than 1. So the system splits into a very interesting couple of equations. The first one is hyperbolic. In fact, I had to give initial condition for chi. But the second one becomes an elliptic equation for psi. And it's very interesting because chi, being hyperbolic, will propagate. So it may have like a wave solution. But because of the coupling, the elliptic equation psi will be determined by boundary condition, but having a source, which is chi. So the second equation is an elliptic constraint on each constant t tilde slice. It requires special boundary condition, not initial data psi dot. And that's the crucial point of these theories. Okay, in the lecture notes, I also explain a bit the green function for the elliptic operator, decays exponentially, so that the shadow goes to 0 exponentially. And what about the complex roots? Essentially, the remote function diverge at a special infinity, but setting the special boundary condition set their amplitudes to 0. The mode psi, we call it shadowy mode, and it cannot be neglected. So what I mean by this is that the dynamics is still a system of coupled fields, chi and psi. So we cannot just set psi to be 0. We will get an inconsistency. But still, it's a coupled equation of motion. And but still, psi has an elliptic equation. No initial condition to impose. So the shadow mode is not an additional wave carrying independent initial data. It is a specially non-local response fixed on each preferred time slice by an elliptic constraint and boundary conditions. So what it means that as chi changes with time, at any time, we will have to solve the elliptic equation. All right, so we can, that was a 1 + 1 dimensional model, which was, without gravity and introduced to understand more or less what's going on. But of course, there are 4D models, covariant. And one of the simplest one that I put here is in equation 18, where we have a p of x term, qx times box phi, and then we have this minus c x phi mu, which is essentially for the version of the model that explained before. A4 is minus cx, A5 is c, f is a constant. So indeed, this action satisfies the U degeneracy condition, but breaks covariant DHOST because Xi is different from 0. So we have a D2, for instance, different from 0. So when a homogeneous freedom networks work background, the Xi operator vanishes identically. Okay, it's like before, this object does not add anything to the background. So the background is purely due to P of x and Qx, what I call here the kinetic gravity braiding. Pitfall, a background-only code cannot distinguish this U-DHOST model from its Xi equal to 0 DHOST limit. Actually, the background cannot distinguish U-DHOST from kinetic gravity braiding. However, it's not the same thing, because perturbation will definitely be different from this kinetic gravity braiding. So the U-DHOST character first appears in inhomogeneous perturbations. All right. In unitary spatial gauge, perturb lapse alpha shift chi and special curvature zeta. Now, What does it mean, this sentence here? Okay, now we have this for the theory, and I want to study, and we said that the background is exactly the same as kinetic gravity braiding. But the perturbations I claim are different. So we should study the perturbations. Now the perturbations, so for this theory, it's natural because phi is time-like anywhere, anytime. So this theory introduces a preferred frame, and the preferred frame implies the choice of phi being function of time. That's exactly the unitary gauge. But in linear perturbation theory, we should also, we can impose an extra condition coming from gauge choice that the three part of the metric is diagonal. After doing that, the scalar field has no perturbation because we chose phi to be time at any order in perturbation theory. In particular, on any background, phi can be chosen to be function of time. Anytime, anywhere. So, okay, we choose this kind of, so delta phi equal to 0, and then the metric, the three part of the metric is diagonal. So, but the metric still can be, has three perturbations available: the perturbation of the lapse, the scalar part of the contribution from the shift vector, and the spatial curvature zeta. Okay, here I consider only the scalar perturbations. Now, the momenta of alpha and chi vanish. Okay, so we don't have terms alpha dot and chi dot. Preservation produces two secondary constraints. So the phase space count is, we have three fields times 2, 6, minus two secondary constraints, two primary constraints, 4, and then 6 minus 4, 2 divided by 2, 1. One scalar mode. The theory, of course, has also tensor modes, but here we were discussing only the scalar sector. And what's interesting here is I'm going to write down the lapse secondary constraints has the form as follows. So we have an interesting term, which is a Laplacian, which is proportional to xi. And then we have a term which actually depends on other terms, which does not vanish in general when xi equal to 0. And we have a right-hand side. Zeta, and p zeta is the momentum conjugate to the zeta. Again, this is an elliptic equation that requires setting boundary conditions. For xi equal to 0, we have indeed the DHOST. Lapse is fixed algebraically. So we don't have any Poisson equation to fix alpha, but it's purely algebraically. And for xi different from 0, we have U-DHOST. It is fixed by Poisson type elliptic equation. And we had to put to define alpha on a boundary. And this is a non-local choice. We don't fix alpha at one particular event, which means point in space and time. The homogeneous solution to this equation is the cosmological shadowy mode. Now, I reported here a bit of Maple code. The Maple code that you will see this U-DHOST opt. Opt means optimize. I try to optimize in terms of time. It studies a general shift symmetric U-DHOST, but it's general. I mean, general but shift symmetric, because most general, maybe it was a bit difficult to optimize, but this part can be optimized. Okay, so I also put here some code, and just for the, I don't put too much code because it would take only 1 hour to explain the code. But okay, but let me tell you more or less how it works, the code. So then when you are alone, and if you have Maple, you can run it, or with the friends in a pub or whatever. So I use packages, a differential geometry. I use another package, tensor, which are defined in Maple. I chose to use here this differential geometry package, for which I had to set up my manifold by this command DG setup, which requires now 4 variables because I am in a 4-dimensional space-time, Tx, y, z. And now I define the perturb metric in unitary gauge. So eval dg means just, so dt is nothing but the tensor dt c times dt, okay? It's classical tensor product of 2 one-forms dt. And the same thing, dt dx, dx dt, dx dx, dy dy, dz dz. Here I simplify myself by assuming that the perturbation are dependent not only on time and also in space, but only along x. And the reason for that is that I know that in linear perturbation theory, all the modes decouple from each other. Therefore, modes which go with different k will not mix, and therefore modes with the same k will mix. So I choose all the modes to be purely propagating the x. This is a restriction, but it doesn't restrict the analysis. Okay, so then I have this, as I said, the metric is purely diagonal. And I have a lapse perturbation. And I have a perturbation from the scalar modes coming from the lapse, the shift. D2 means the derivative with respect to the second variable. In this case, this will be di chi, where I is only along x. So we expand the scalar field phi to be function of time plus epsilon delta phi. But later on, we will set this object to be 0 and calculate covariant derivative and invariance. Okay, so I put this one, phi, epsilon phi delta phi. So this is the beginning. I don't put equal to 0 also because field covariant derivative. So this would be nabla mu of phi, nabla mu, which is covariant index. I introduce the inverse metric, and then d phi u, this is just a name, by the way, whatever in the left-hand side of this assignments, this is just a name. So d phi u, it means just d, for me, u means up and d means down. So I had to raise lower indices with the J inverse of d phi down, the first index. So I also define the x scalar, which is the contraction of nabla mu down, nabla mu up. The contraction comes with contract indices, the first index of this and the first index of that. And that would be my x. Now this is the second derivative. This will be nabla mu, nabla nu. Okay, because I take the covariant derivative, which puts an index, covariant index down of already d phi down. And then I can construct my first L1, which is the contraction between d phi down down, d phi up up. Yeah, of course, if I up, it's not written here explicitly, but it's clear what I did. No, I raised the indices by using contrast indices. Then I can construct the 4-dimensional scalar in this way. I can find my determinant of the matrix. And then I have the action here after having also introduced, of course, L1, L2, L3, L4, L5. L1 already introduced, by the way. And you notice I put shift symmetric case for which all my functions are purely function of the x, not phi itself. Now I wrote the full U-DHOST degeneracy condition, which is this object here, which is a function, you notice, of x scalar. But x scalar is d mu phi up, down. But inside there are perturbations. So this degenerate condition has perturbation. And not only because of d mu phi may have perturbation, but the metric has perturbations. So this degenerate condition is a non-trivial function of the whole perturbation variables. So I can expand, and of course this degenerate condition must hold for the theory. So it must hold order by order. But here we're going to only consider this degenerate condition background, this object here. By extracting the epsilon part of the action, we vary it with respect to alpha, zeta, and delta phi to find background equations. So, yeah, maybe I should have said, did I? Oh, yeah. So you notice that apart from this field, I have also an epsilon. Epsilon is just a number, which is supposed to be small, that I use it as a parameter on which I do a Taylor expansion. So after all, my action, which I called axio, is actually my Lagrange density, because I have square root of minus the determinant of the metric. So so axio in any case it's not a matrix, is a function, scalar density, but I can expand in terms of epsilon. So I will have an action at the level of a mini superspace when epsilon is equal to 0. Or I have an action linear in epsilon, as in this case, because I expand up to second order, and then I take the coefficient in epsilon. And then I find my equations of motion for alpha, and this will give me the background equations of motion. This background equations of motion calculated in this way should be compared and checked against the equations of motion coming from mini superspace. In any case, we extract the kinetic matrix, we take the epsilon square part of the action, and that will be the action quadratic in the perturbation. Use heavy integration by parts routine to isolate the terms like that. You notice that I will have terms zeta dot squared, alpha dot squared, and zeta dot alpha dot. And this tells me, ooh, this one looks like I have extra degrees of freedom because this is a kinetic matrix. And I would expect only one scalar to be propagating. But okay, so let me find this kinetic matrix, the coefficient of the zeta dot squared, the coefficient alpha dot squared, and the coefficient of alpha dot zeta dot. Then I can build up my condition, my determinant, and this is determinant, k11, k22 minus k12 squared. And then I notice this is proportional to the degeneracy condition. So therefore, because we impose a degenerate condition is 0, also the determinant will be 0. So what it means k22 is equal to k12 squared divided by k11. And so this is the famous theory definition that was done as usual, okay? If I have k11, k2, k11, k22, k12, k12, the eigenvector with non-zero eigenvalues is 1, and then, it's minus K1, 2, K1, 1, and 1. Okay, so when I multiply K11 times K11 times this thing, I will get minus K12 plus K12, it will be 0. And the other one will be K22 minus K22 times K22, yes, time K12, sorry, K12 times this, which is minus K12 squared divided by K11 plus K22, and this will be 0 because the determinant will be 0, okay? So you notice this object here is really related to the presence of the eigenvalue, eigenvector with 0 eigenvalue. And this one you should consider as, this is a Felice definition in terms of zeta. Zeta is the new zeta times this, and the other field, which completes the Felice definition, is alpha is equal to alpha. So you notice that the column in alpha is minus K12 divided by K11 and 1, which is exactly the eigenvalue with 0 eigenvector. Sorry, the eigenvector with 0 eigenvalue. Okay, the constraint equation in the shadowing mode. After diagonalizing, okay, so the fact that I do this Felice definition removes the terms in alpha dot square. It also removes the terms in alpha dot zeta, zeta 2 dot, which means that now alpha becomes, we can actually remove it. And in particular, we will not have dynamics for the lapse. We then integrate by parts to isolate the coefficient for special derivatives like the Laplacian dx square alpha. Again, this is one dimension, but of course, this is nothing but the Laplacian of alpha. So we will have these two terms here. In general, B1 and B2, which are the coefficient of the, you notice I have this Laplacian square of chi in my Lagrange, and this gradient square for alpha. So the action, I wrote, as I told you, I gave you the maple file, and so this was just how can I say, a short recap of what you may see in the maple file if you open it and run it. But in the end, this quadratic action can be written in the following form. B1, B2, B3, B4 are coefficient. Some I wrote it, but actually 0. And they're 0 either on the equations of motion or by using the degeneracy condition. Okay, and but what's interesting here is that this nabla and alpha don't have kinetic terms. All the kinetic terms may be shifted into the field zeta 2, which is going to be the propagating mode. Now, this action, of course, like that, it's in principle really it needs elliptical equation to be solved. But we can go in Fourier mode, and because implicitly Fourier modes in the field doesn't blow up at infinity. Okay, so in Fourier map alpha, k, and zeta 2, I rename it like alpha, ch, and zz2. And then every nabla square goes into minus k squared. And now k squared becomes just a parameter. And therefore, my action becomes a function of the Fourier transform with the nabla square replaced by k squared. And therefore, we can actually integrate out algebraically in terms of the Fourier modes. And what we will find is this what I call reduced Lagrange, where QS, I would call it is the no-ghost mode. That must be positive and non-zero. And we have CS squared, which again must be positive and non-zero. this dot that I am left with is because here I took sub-horizon approximation when k is much larger than k over a is much larger than the Hubble function. So in dots are terms which are suppressed, either they go with k to the 0. So in the sub-horizon limit, this part dominates. And out of this part of the Lagrangian, we can actually deduce these two constraints. Okay, so I almost finished. So the theory U-DHOST breaks covariant degeneracy but maintains it in unitary gauge. You notice the trick of the Stuger field, which allows essentially any theory written in terms of time and extrinsic curvature and Laplacians in terms of a scalar. Cosmology, and we saw that the apparent extra mode is a constrained shadowy mode fixed by elliptic boundary conditions. Cosmology background is often indistinguishable from standard also KGB, but perturbations reveal modified spatial constraints. In practice, MAPLE automates the ADN decomposition, integration by parts. A trustworthy RAM must also display and inspect the zero residuals and assumption introduced by solve. Okay, you may have a look into the MAPLE code. And I think I finished.
Okay, thank you, Antonio. Okay, any questions about? I have one questions about at the beginning when you were talking about stackable ticks. And I don't. Maybe I can catch some. When for stackable tick, you have a kind of kinetic term have a gauge symmetry, and then you have a mass term, and you introduce the fields to restore gauge symmetry, right? Okay, and in this case, how you use stackable tick in order to construct the covariant one?
Yes, that's a good point, actually. So, yeah, that's a very good point. So, okay. Okay, there is a procedure, okay? It's kind of a recipe, if you want. For instance, here I assume alpha 1 to be function of time only. And the fact that it's alpha 1 is a function of time only means that alpha 1 is a function of phi only, because phi on the unitary gauge becomes time, or function of time. The other terms are less trivial. For instance, we have this k, the trace of k, actually. Now, the trace of k, if I have, if I had this Stuger field, where I assume that this action is found by assuming the Stuger fields to be time, then k is coming from phi foliation. So then I had to find k in terms of mu, where mu was coming from phi. So automatically, this gives me this kind of part of the. Now this is a covariant object because mu I can rewrite it into this term here. So piece by piece, I am going to reconstruct the action that I have. If you want, you need a dictionary. How to express the object you use in terms of your mu or your scalar field. But after you have the, you had to use Gauss Coordinates equation, because we had R3, and R3 in this slicing thing, it's R plus K squared minus K mu mu, like this, where all this mu coming from the phi foliation. So then you can reconstruct piece by piece into this kind of way. In general, if you see something like this, okay. So for instance, what do I see here? This is an action breathing in ADM. Then I would say, okay, there is a scalar field. May not be enough, but there is a scalar field out of which we may be able to write down the full covariant action. Why do I say we may be able? Because maybe we are not, how can I say, we can break diffeomorphism not only in time, but also x, y, z. So for instance, suppose this alpha 1 was a function of t, x, y, z, then what do? Well, we can introduce a scalar field for any variable. Phi 1 would be time, phi 2 would be x, phi 3 to be y, and so forth and so on. So we will have multiple fields. We will need multiple fields. But notice that one of them will be time-like, because t, and the other one should be space-like, because must be x, y, z. So the construction is not trivial, but, you know, typically you have a dictionary.
Okay, thank you very much. Any more questions about this? If no more question, or you have one? Okay.
The equation out of the scope. Don't you have a code in GR tensor?
Yes, GR tensor. Then there is also, I forgot, exact. I mean, please choose the code you work the best with. I mean, so this one is up to you. This is up to the. I talk to the student, up to the students to pick up the code that you like the most. I use this one because, to be really honest, because I had old code and I didn't want to rewrite new code. So so then I just, you know, made a bit of optimization of an old code that I had. But of course, you can use several other packages.
Okay. So we have about 15-minute break, so that we come back again about 2:20. Is okay for you? Internet. Okay. 2:20 we come back.
Bye.
So now is the time for the full lecture. Just waiting student come in a bit. But
So should I start?
yeah, I think you can start now. Because I also waiting for the student come, but I think you can a little bit start.
Don't worry. I'm not in a hurry. So if you want, we can wait 5 minutes or something.
Yeah, and Kampi also come. Okay, that's coming. Yeah, I think you can start now, Antonio. Yeah.
Okay. I will start. So up to now, we saw theories which have constraints. So the theory were built to have some properties, and these properties were achieved by setting constraints. Now, the constraints that we got were not, how can I say, were done at the level of the Lagrangian by choosing some particular functions. For instance, the degeneracy condition for those we set constraints on the functions AI, saying less restrictive with the U-DHOST. But there are other kind of constraints that you can use to restrain a theory. Let me give you probably one of the simplest example. Now, suppose you have a particle which moves down. Then, using Newtonian mechanics, we fix what is the force on the particle, and then we give initial conditions. The problem is solved. as long as we can solve the differential equation, but that's another issue. But we can put a constraint. For instance, we can put the level of the Lagrangian in spherical coordinates. I put a Lagrange multiplier, lambda, which multiplies little r, which is the radial coordinates, minus capital R, which is a constant. So the field lambda sets the radial coordinates r to be capital R. This is a constraint that we set at the level of the Lagrange. This constraint removes 1 degree of freedom because we don't, R is not anymore a free variable, but is constrained to be capital R. We can play this game, and now essentially this is a particle which moves on a sphere of radius r, and we can play this game. The point is that we should be careful which constraint we set, because if we over-constrain the system, now the system moves on a two-dimensional manifold, which is the surface of the sphere. But one has to be careful because, for instance, if I add another constraint, I may completely cancel the solution. So using constraints, it's interesting, but needs to be done with some kind of logic or philosophy. I don't know. So usually, what we want to do is to have an idea in mind. What do we want? Because constraints usually remove something. As we saw, the degeneracy equation, we're removing the Ostrogradski ghost. Now, in this, I'm going to talk in this lecture about the minimal theory of massive gravity, MTMG. This was a theory introduced, I think, more than 10 years ago with Professor Mukoyama. And is and still remains an interesting possibility for a massive graviton. So I think it may be worth discussing. Okay, so
sorry, what do you mean by minimally?
Yeah. I'm gonna talk. Okay, so minimal for me will be theory with which have in the gravity sector only two modes. Okay. So GR is a minimal theory. Okay. So I want to introduce a minimal theory of massive gravity. So introduction, and for that I need to set constraints. Introduction.
But in massive gravity, the number of modes more than two. Am I right? Yeah.
Yeah, that's true. So in order to do that, we need to break Lorentz invariance. Okay, it's a famous. Yes. In any case, okay, so yeah, that's true. I mean, exactly. I mean, massive gravity would have 5 degrees of freedom, and we want a theory with only 2 degrees of freedom. Okay, let's start with I'm going to start with introduction, goes in massive gravity. Also, I'm going to introduce this minimal theory of massive gravity. And for what we are going to look into that, we're going to talk about free-diameter Lorentz work background and perturbation gravitational waves. And a little bit of, very little of maple practice. Okay. So in general relativity, the Hamiltonian is a linear combination of first-class constraints. Okay. Here, n is the lapse and I is a shift, and for me they are just non-dynamic Lagrange multiplier, enters linearly and sets for constraints. For constraints, they are all first-class constraints. So what it means is that they eliminate 8 degrees of freedom in phase space, 4 times 2. So if my metric is here, the only variable is the 3D metric, gamma j. So I have 6 independent variables, a 3 times 3 metric, and then 12, 6 times 2, 12 phase space variables, minus 8 is going to be 4, divided by 2 is 2. Okay, gives exactly 2 physical tensor modes from the region of 12 phase space variables of Hij. Now, generic mass and gravity. Given the gravity on a mass, breaks diffeomorphism invariance explicitly by adding potential UGF. Now, what is this? Yeah. Okay, let's discuss a bit. This is related to the first question that I received. Now, when we have electromagnetism is a Yuan gauge invariant. However, if I put an explicit mass to the vector field, I lose such an invariance. Okay, I explicitly break Yuan gauge invariance if I put minus mu square a mu a mu. And of course, this will change degrees of freedom, blah, 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 but I lose symmetry, first of all. Now, in gravity, it's interesting because in gravity, suppose I have this gamma ij, I need to set a mass term. But the gamma ij contracted with gamma ij is a constant. So it doesn't give, this is a bit naive talking, but it doesn't give an explicit mass term. In order to give a mass term to gamma aj, you need to introduce an external field. Of course, you can introduce extra fields, but an extra fields will be still extra degrees of freedom. What I'm going to do is I'm going to introduce this F field, which is an external field. An external field breaks explicitly diffeomorphism invariance because something functional time, something functional t, x, y, z, and that F is what we call a fiducial metric. So G will acquire mass thanks to a fiducial metric. In any case, a generic mass term introduces nonlinear independent, or in principle, if I introduce this general potential term, generic mass term introduces, this is G, the 4-dimensional G, okay? And inside G, there is the lapse and shift. So one may say, hold on a second, but if you do that, what you are going to do is you're going to break at some point this nonlinear dependence on n and I. So the constraints h not equal to 0 and hi are lost. So all these components of special metric hij become dynamical to tensor, to vector, to scalars. And one scalar mode has negative kinetic energy because that would correspond to the Bulwer desert ghost. Okay, but this that
Sorry, those extra modes are not physical mode. Am I right? Or it's just a mathematical decomposition of the metric?
there's extra modes. What do you mean? There's extra modes?
I mean,
No,
you say
Okay.
please go back to the previous slide.
Uh-huh.
Yeah, here you say do two tensor, two vector, two scalar.
Because introducing an external field, I cannot use any more gauge fixing. I already fixed the gauge. Okay, so let me go back to the previous slide. Remember that I had a alpha I, which is function of time. So alpha I is a function of time, is an external field. So if I want,
I mean for a diff invariant, for example, quadratic theory, where if you linearize that theory, also you have a massive terms.
But that's due to some. Okay, I think you are saying if you take I don't know, Arminu, something like that, or y squared.
While square
or R square. What do you mean by
yeah, I mean quadratic term. Okay, while square. Okay, yeah.
Okay, so so while squared there, it's a different object because while square will introduce this extra derivative and introduce this Ostrogradski ghost. It's a different kind of, but that theory is still for the diffio, and you can use those for constraints to, for instance, remove degrees of freedom. But as soon as you introduce, external fields, then you lose, because it's like in the previous slides, when you have alpha I of time, and you already fixed the gauge for time, because phi is equal to t. This is your gauge fixing. So you cannot use again the same freedom, and therefore you cannot remove those Hij that you would remove by using, in this case, gauge transformation, or what you mean. You lose the constraint to be first class.
Yeah, okay. Yeah, okay, thank you.
Okay, so we have this. So we would expect to have more degrees of freedom, actually. Now, Deram, Gabadadze, and Tolli discovered a specific potential function of this GF, which was keeping Hamiltonian linear in N. After shifting the definition, but okay, there was in not introducing, so was keeping the object linear in N. So this produces a primary constraint and its secondary partner. The pair projects out the DHOST. Now, what does it mean? It means that in principle, we would have those 6 degrees of freedom, but by choosing a particular expression for this interaction between this external field and G, it's actually possible to find that N becomes linear. So N sets a constraint. If N comes non-linearly, its equation fixes N, but it doesn't set a constraint. So if comes linear, it sets a constraint, a primary constraint, time derivative sets a secondary partner, and therefore you have two constraints more, remove 1 degree, and then you are left with 5 degrees of freedom, as you would expect in this case. Now, okay, the external field F, how do we choose it? The point is the theory does not tell you how to choose it. Which is then how possible. But this is similar. This is similar to. Let me go back again to the Zuckerberg field trick. So if you have a function t, which is your external field, alpha 1 is equal to t, then you say, okay, I promote my t to be a scalar field, phi to be t, then I have alpha 1 is equal to phi. But nothing prevented you to start with a theory which was alpha is equal to t squared. And then if you do the same mapping, this, of course, alpha 1 changes. So as much as we can change the function alpha 1, we can also change the external field f. Different f, in general, will lead to different theories. Like different alpha 1 means different DHOST or U-DHOST theory. Same thing here. So therefore, people introduce at first the external field in the simplest possible way, I mean Minkowski. So F mu was eta mu. So there is no dynamics because it's an external field, it's set by hand. So standard DRGT has no, but the problem, I mean, this is just a choice. That theory had a property that were not existing exactly homogeneous and isotropic solution with a specially flat Friedel method of Benson-Walker physical metric. So what does it mean? If I set this Minkowski reference.
So sorry, I didn't realize in this part. In general relativity, we don't have a preferred background because metric itself is a solution for the field equation.
Yeah, true.
And
I'm talking about F, the fiducial metric. You need to introduce an extra metric, which if you introduce an extra metric, then you say, okay, I have two metrics, so two tensor. But now you introduce a fiducial metric to be, again, as alpha, the DHOST condition, okay? So function of time, x, y, z, and not function of the gammas of the. So this is not generativity. This is not generativity. Forget about it. This is completely different from generativity. Okay, so open. So we had to give this reference metric as part of the definition of the metric, and therefore there was also an interesting thing because these theories, even if we were getting so promoting Minkowski reference frame to be a given Friedel method of Benson-Walker metric, okay, with a scalar, with a scale factor given it as a function of time. This was allowing especially flat Friedel method of Benson-Walker. But they still had some strong coupling issues because some modes had zero kinetic term. So what does it mean? On known self-accelerating DRGD branches, the quadratic kinetic coefficient of two vector modes and one scalar mode can vanish. So we have 5 degrees of freedom, 3 of them had strong coupling. A vanishing kinetic coefficient is not the statement CS squared equal to 0. The quadratic action no longer determines a sound speed for that mode. So it's really the full kinetic term vanishes. And it's not a constraint, it's an object which should exist but doesn't at the linear level. The modes still exist non-linearly, so the perturbative expansion becomes strongly coupled. Yes. Now, myself with Professor Mukoyama, 2015, bypassed these problems. We took a radical approach. We explicitly break 4D different Friesen invariants in the action. How do we do it? Enforce new constraints by hand to eliminate 3 problematic degrees of freedom, 2 vector and 1 scalar. Is only to healthy massive tensor modes. How do we do that? Okay, this was related to something that one of the students probably, or the postdoc asked at the beginning. I would put an important distinction, the coefficient of Q dot square vanishing on a solution, there would be a strong coupling. And here, distinction of a primary secondary constraint pair removes Q and PQ from phase space. And TMG changes the generic nonlinear constraint algebra. Its absent scalar and vector gravitons are removed variables, not zero kinetic variables. Okay. How do we do that? Okay, let's start. So we first define the canonical fields, and we find it easier for this analysis to introduce the Vilbine. And what is the Vilbine? The Vilbine is an object, okay? This object here, as you see, as a lapse, as a shift, and then has 3D spatial Vilbine. So what does it mean here? This object here is a 3 times 3 metric, lapse and shift. If you take EA mu with another EA mu, contract with the Minkowski metric eta AB, what you will find that this takes the form of ADM form, where gamma is given by the square of this 3D Vilbine. So if you do this, you put the square of E alpha, A mu will give you G mu in ADM form. Point is, which is interesting, that you can, this is not the only form for the Vilbine, which gives G mu, because you can use a boost, because the boost is independent, eta mu doesn't fill the boost. So the boost is a symmetry. So you get G mu no matter how you boost this object in the indices A. Because we have a fiducial metric, we also introduce a fiducial Vilbine where M and K and E are given functions because it's an external field. It can be function of T, it can be function of Txy, Txyz, whatever. But it's an external field. No dynamics, it's put by hand. It's like alpha 1, alpha 2, a function of T in DHOST. And in particular, we have essentially lots of choice to do. Now, it's true, but remember, we don't want to destroy our solutions. We don't want to over-constrain. For instance, if I want a cosmological solution, M must be function of time because it's a scalar, and therefore it cannot be function of Txy, even though it's put by hand. If I put by hand that M is a function of T and X and Y, Z in general, this will make it possible to have field dynamic Robinson Walker backgrounds. So what it means that this external field will be incompatible with homogeneity and isotropy. It's okay, but then we had to explain why cosmology is a good approximation at large scales. So we took a very simple reasoning and we say, okay, let's consider all those functions to be purely time dependent. M is a function of time, and K is a function of time, and so forth and so on. Now, as I said, we can still boost this object here because EA can be boosted by a general boost, again, external boost in this case, to give me the same fiducial metric F mu nu. So up to a boost, these are the triangular ADM form. Now, what we do, if I have only, let's say, GR, this would be totally okay, would have a boost, everything would be totally consistent, and we still have 2 degrees of freedom. So it will not change anything. The point is that DRGT people introduced the coupling between G and F. Now, that coupling G and F does not necessarily introduces the coupling in terms of, so there is the Will buying going on there. So that term there may actually be dependent, possibly, on the boosts. And in fact, what we find is that if we replace this triangular form for ADM in the RGT, we get this object here. And it's interesting because, as you notice, there is a term. This is the standard term, which I will call Einstein-Hilbert term. And then there is a term which is linear in the fiducial lapse. This is a function of time. And then there is a term which is linear in the lapse. But you notice that this remained linear in the lapse. Okay. So we call it this precursor theory. Now we have 9 configuration variables because E, I, and J. Notice there is, in these terms, there is no fiducial or physical shift. H0 and HI are only functions of the 3D Will-Buying, of the fiducial and the physical metric. Okay, so the canonical fields, special, Then we have 9 configuration variables, this one, because the fiducial are external fields, so no dynamics. So we have 18 dimensional phase space. We have 12 independent second-class constraints on a generic background. So the number of degrees of freedom, 18 minus 12, 6 divided by 2, 3. So this is the action. One should go through the Lagrangian, to the Hamiltonian, find the whole constraints. Constraints algebra, and one finds there are 12 independent second-class constraints. 3. So instead of 5, the choice of this triangular form, remove 2 degrees of freedom. Remains 1 extra scalar. And the extra scalar would still have 0 kinetic term on field-dimensional Walker. So it's not good enough. We should do more. So what we add is, by hand, we added 4 constraints. You notice that this is the Hamiltonian or the precursor theory, the theory that I told you before with the triangular form for the Will-Buying. And then we add these 4 constraints here. I mean, 4 constraints. Why 4 constraints? Because actually, among the 12 previously found constraints, 2 of them were included into this. So what we are adding now is two extra constraints. Two extra constraints means that we are removing an extra degrees of freedom. And therefore, we will have only 2 degrees of freedom. The theory becomes minimal. How did we choose this C0 and Ci? Okay. I think I wrote, okay. Here we put lambda R Lagrange multipliers enforcing exactly 2 new independent constraints. Notice that the Hamiltonian is extremely simple because you have n and I. This is linear in M, this is linear in M, but this is just a function of time. We have these constraints C0 and Ci. So the equations of motion, of course, will be the constraint R0, R0 minus m squared h0 to be 0, Ri, C0, and Ci. This m is a fixed function, is not a Lagrange multiplier, so you don't have the equation of motion h1 to be 0. But this term will contribute because inside here there is 3D Vilbine. Okay, so from the 18-dimensional Vilbine phase space reduced by 14 independent second-class constraints, 18 minus 14 is 4 divided by 2 degrees of freedom. And the reason why the tensor mode remains because these constraints are purely scalar and vector. So the RGT 5 modes, preferred frame, it goes into 3 modes, precursor theory, and 2 new constraints, 2 tensor modes. Now, this theory is a bit old, but, in terms of massive gravity, it's still an interesting possibility. But I mostly talk about this because I think it's a good example of, constraining theories. Now, having said this is our action, our Hamiltonian, when we want to find the action, we have to do a Legendre transformation, and the action transforms into this object here, which is a bit complicated, but not so extremely complicated. And I want to understand what happens on a free-element Rubens-Walker background. Now, the gamma tilde here stands for F, the fiducial metric. A tilde stands for a given dynamic, a given scale factor with some given dynamics. Gamma ij is instead the free function of time. X is just the ratio between these two objects. Then we define parameters, which is the Hubble factor. The Hubble factor for the fiducial metric, again, this object here must be considered as a given function. And then we define this R to be this ratio for convenience. Now we have this kinematic identity. If we take this dot here and replace into this stuff here, we get x dot over x is equal to this mhf minus nh. When x is equal to 0, when x dot equal to 0, when this ratio is constant, which means that A follows A tilde, because A tilde is given, of course, we will have a ratio between the two scale factors. It doesn't need to be like that, but maybe possible. Now, special matrices are proportional to identity. So this K was actually related to gamma tilde inverse gamma square root. And therefore, what we get is this, I have object which defines the theory, which actually diagonal at the level of the background, of course, which is in this form. Theta ij reduces to this objective. Notice this mat cal is a kind of ratio between Okay, it's the relation between the 3D Vilbine. Kij is nothing but extrinsic curvature in a flat spacetime. So this theta ij, which is part of the theory block, becomes proportional to gamma ij on the background and times 2jx. Jx is this interesting combination that, if you know mass and gravity, it comes out a lot of times. Now the scalar constraints reduce to this C naught on the background, which must be set to be 0, as this quantity must go to 0. And now we see immediately that there are two branches. In one branch, J is equal to 0. M cannot be 0 because M is a given non-zero lapse. But J can be 0. And J means 0 means that X is a solution, if it exists, given by C1, C2, C3, which are theory coefficient. So in other words, if J goes to 0, X becomes constant because it's just a function of C1, C2, C3. If X is a constant, remember that we had this relation between, when X equal to dot, between the Hubble functions. But another possibility is J is different from 0, but actually you have H is equal to X HF. These are the two possibilities inside this theory. All right. We can find the mini superspace Lagrange in this form. And where Ux is a polynomial in X, Px is another polynomial. We have this object here that vanishes whether J goes to 0 or this object goes to 0. But in general, it looks like we have a standard term and then something which depends on little m squared and to the fourth. And you notice there is a part which depends on this thing here. This is the matter Lagrange, in case we have matter. And then a term, two terms which depends on lambda. Lambda and lambda. Okay. Now we can then rewrite the Friedman equation in a more the Einstein equation. This is sorry. I'm sorry. This is the Friedman equation. Is the Friedman equation which is found from the mini superspace Lagrange when we vary with respect to the lapse. And of course, this term doesn't have lapse inside, so it doesn't contribute to that. So the Friedman equation has these terms here, one part which I rho, which is the standard matter fields, rho g, which is this object here, and rho lambda. I call it rho lambda because you see you have lambda inside. Now, if we take variation with respect to lambda, here's the branch equation. Again, as you see here, we have J equal to 0, and possibly this quantity equal to 0. But as you notice, this looks a bit different from the constraint before. Indeed, the constraint before was setting this object to be 0, and Jx was different from 0. This implies that lambda is equal to 0. Lambda equal to 0 on the background can actually be derived in several different ways, but all of them are consistent with each other. In other words, on the Friedman electronics worker, lambda is 0. Therefore, these two objects are 0. And then what we get is that rho g gets this function here. This function is a function of x only. Rho lambda is 0. Rho is the standard matter. And x is interesting because x, remember, there are two solutions, when j equal to 0 or when this object is equal to 0. Now, when j equal to 0, we said x is a constant. Therefore, this polynomial ux becomes a constant. Therefore, this branch behaves exactly like lambda CDM because this becomes a cosmological constant. What changes the tensor mode will be different from the one in lambda CDM. The other option was this relation, this non-trivial relation for the Hubble factor. But what it means that now this rho g becomes dynamical because x is time dependent. So we have now a possibility for time dependence in the massive gravity sector. Okay, Jx equal to 0, we call it self-accelerating branch because it gives automatically a cosmological constant, acceleration. And the bracket term, this one, because lambda equal to 0, actually gives the normal branch. We call it normal because it doesn't need to be automatically self-accelerating. We can find also the equation of motion for the scale factor, which gives effectively the second Einstein equation. And we will have, again, this object here. And Pg and P lambda are effective pressure from the mass potential and the constraint. We can combine the equations of motion. This is similar to finding Bianchi identities. Just combining the equations of motion is a cubic polynomial in lambda. Again, for consistency, lambda equal to 0 is the solution. We can find lambda equal to 0 purely from also in the mini superspace Hamiltonian formalism. Maybe it's even simpler. Okay, so let me study a little bit this self-accelerating branch. On a continuous branch associated with an isolated root, Gx equal to 0, implies that x is equal to constant. Eliminating C3, okay. Eliminating C3, why eliminating C3? Because if you remember, Jx was a combination of, setting Jx equal to 0. But of course, this can be thought as solution for x, but x is a constant. So then I can just solve for C3. Okay. So eliminating C3, it gives that rho g is this object here, which is a constant, and Pg becomes minus rho g, as you would expect from a cosmological constant. On the generic self-accelerating branch, consistency fixes lambda to be 0, so rho lambda and P lambda equal to 0. Recovers GR with a cosmological constant. Self-accelerating originates from graviton potential. So that would be a way to generate a cosmological constant from massive graviton term. But this doesn't solve the cosmological constant problem, but gives some interesting possibility. For j different from 0, the bracket term implies that lambda, which is 0, is equal to x hf minus h. Substituting into EB is a factorization with the regular normal branch is this object, lambda equal to 0, and lambda P lambda equal to 0. So evolution of x is entirely kinematical. Right. So what we have is x dot divided by nx is equal to hm over nx minus 1. And this was what I call R. This is given by this. No propagating scalar, but the equation of state Wx can differ from lambda CDM. Thus supplies one scalar mode, gauge invariant, density, contrast, delta m. Okay, now because I don't have any scalar mode, when I introduce matter degrees of freedom, we should check how the action changes, if it changes. Self-accelerating branch, exactly the GR growth equation. Okay, so if we use the self-accelerating branch, I don't see any modifications in the GR growth equation. But the normal branch, yes. The normal branch, I have a non-trivial, no ghost term, and the non-trivial, notice that still it doesn't propagate, dust. Okay, the speed of propagation is dominated by the mass term, but we have, of course, Jeans instability. So friction G effect, it can differ from GR. We can realize weaker gravity in principle, if we want. Second order action from tensor mode, the tensor mode acquire a mass term. And this is actually, I mean, this was the whole point, is to give the tensor modes a mass. Speed of gravity, notice, is in the high K regime. So when the mass is negligible, the speed of propagation is 1. So it means when the graviton is ultra-relativistic, it propagates with speed equal to 1. So to avoid the GR 1708-17, we need to impose that the mass is small enough. And indeed, when we set mu of time to be of order of Hubble factor today, the constraint is well passed, satisfied. So massive dispersion, we have the massive dispersion in the adiabatic approximation. So in any case, so that's, we are almost at the end of this last, no, this last but one lecture.
Hello, Antonio. Can I ask you some about maybe the last 2 slide period?
Okay, sure.
How can you find matter perturbation in the level of Lagrangians here? What is the field you consider? Or
Very good. Yeah, very good. Yeah. So this theory affects only the gravity sector. The matter sector is exactly the same as in general relativity. In particular, general relativity, I can have, here I consider perfect fluid Lagrange. But you can assume any matter, because the matter sector is purely, in the matter sector, of course, you can do, the matter itself, when you change your fields, that is purely covariant. The Lagrange or the matter fields are covariant. So you introduce your fields as you would do for, let's say, a perfect fluid in this case. You will have a current, you will have energy density, you perturb your field, and then you are right. Because there are no scalar modes from the gravity sector, you will end up only with matter modes. Now here I consider dust for simplicity, because you see this is purely a dust fluid. But in principle, you can choose some other fluid. You can put a scalar field, doesn't matter. You can put anything you want. Now, this object here comes, sure. So after having that, you plug into your action, expanded second order, and it's true that no scalar modes will be arising. However, there will be constraints which are different from the one in general relativity. So what it means is G effective is not the Newton constant, but it will be in general, as you see, also K dependent. But at linear, if you put high K, this is purely constant, and it goes to Newtonian constant. So for high K, this GF goes to GN. But yeah, so the matter field are same.
Okay. Thank you.
Oh, you're welcome. Okay, Then we have the background equation derived are complex and prone to algebraic errors. This is always true, not only for this theory. We can automate this using Maple or GRTensor, or whatever you like, and define the mini superspace action. Very nice exercise also is to find the mini superspace Hamiltonian and find the Hamiltonian equations of motion. The constraint analysis, it's a very interesting exercise. Yeah, so you will get this setup polynomial UX, VX, and JX, and notice that I have a Maple file that does this for the background. Perturbations are more complicated. I have not written the code for that. Use the Euler-Lagrange operator to compute the variation automatically. The supply worksheet prints the 3-row variation and the factor multiply equation. A separate comparison with the hand-derived expressions is still needed before calling an equation verified. Okay, so what I mean is that, so this is a way, but you need, okay, when you have, okay, this is for the students, but for me, myself as well. When you have some theory, and you may look for equations of motion for the background, you find, oh yeah, okay, yeah, I got the background equations of motion. Good, but not enough. You say, what do I have to do more? You had to cross-check. How do you cross-check? You find several possible ways to find the equations of motion. One way, as I said, is this one. You have the Lagrange for the mini superspace, and you find all the equations of motion for all your fields. But you have also the Hamiltonian. So from the Hamiltonian, you can find the Hamiltonian equation and should prove that they are equivalent to the Lagrange equation of motion. Third way, I don't go into mini superspace. I introduce perturbations and I expand up to first order the action in perturbations. Expand the first order in perturbation, integrating by parts will give me the equations of motion for the background. So you have at least 3 methods to find. It's a good practice. I usually follow 2 different ways to cross-check my results. Okay. Now this Maple practice deriving this extra equation is rather complicated in the Lagrangian formalism, but almost trivial in the Hamiltonian formalism, where the solution line by equilibrium is almost automatic. In the Lagrangian formalism, one has to do lots of checks. But for instance, this extra condition, we construct a linear combination of the Friedman, the derivative of the Friedman, second Einstein equation, constraint for lambda, equation of motion for the matter field. And the equation of motion for the matter field is the standard continuity equation, by the way. Of course, simplify, collect, okay. The supplied Maple code does not run this full consistent polynomial check. It stops the vacuum background variation. Okay, so I follow only one way, but there are the Hamiltonian way and the linearizing perturbation way. When we do the perturbation, maybe I want to end with this, the fiducial metric is already an external field, so we cannot perturb it. But we have to perturb all the other modes in the gravity sector. Okay, let me write to the summary. A generic nonlinear mass term carries the DHOST. The RGT removes it, but retains 5 modes and difficult cosmological branches. And TMG breaks Lorentz diffeomorphism invariance to remove dangerous modes. That's why we can have a number of degrees of freedom different from 5. Features exactly 2 tensor modes, their mass parameters must still satisfy stability bounds. Yields a rich background cosmology, self-accelerating normal branches, and has CT square equal to 1 and the potentially testable massive tensor dispersion relation. Thank you very much.
Okay, any questions?
May I check my understanding? Okay. In the construction of MT theory, you first break the for this field maximum invariant to remove constraint in the original massive cavity theory. Is statement correct?
To remove degrees of freedom.
Constraint, yes. Original constraint in
so yes, we had to add. So I would say that we add constraint to remove the degrees of freedom which were present in this precursor DRGT. DRGT has 5 degrees of freedom. Okay.
So constraint you add is top on the original massive cavity theory.
Yes.
Okay. I understand.
Yes. Actually, yeah. So yes, you can think about that. Yes, you can think about that.
But in the MT theory, finally in the MT theory, the spatial diffeomorphism invariant is restored. Not. No. So and what is what will be happen in this case? Theory not invariant under the coordinate transformation, or I'm ready to check for this.
Yeah, that's a very good point. Okay, one way is that there are possibilities there. Okay, so for instance, this answer is very long. Okay, but okay.
Really? Okay.
No.
That's briefly. Okay. Yes.
But the question is very good, and but I'm not so good to answer shortly. Okay.
Because you can breathe because your sound is not so good, I think. Yeah.
Okay. So let me put it this way. So the fact that we break for DFO means that the fiducial metric is anywhere, any place the same. So in particular, if it is a function of time, that function of time will remain on any environment. So for instance, in principle, static black holes will not exist. Maybe a good approximation, but it will not exist as a formal solution of the theory. Another thing to say, of course, as we have done in U-DHOST, we can reconstruct a covariant theory. And the fact that we had to add multiple Stuckable fields. Okay. So this is similar to the construction of some, I forgot the name, but some kind of field theory in fluids where people use multiple Stuckable fields. So something is, so actually it's possible to write down the theory in a fully covariant form in terms of a time-like and 3 space-like vectors. Scalars, sorry. And then this theory becomes this one when you assign to the time to the time-like phi, you call it t, and the other 3 space-like you call it x, y, z. So it's possible to go into a covariant theory, and then you study the theory from, in the typical way. However, three of those fields are always space-like, and one is always time-like.
Mhm.
That's the price to pay.
Uh-huh.
So what it means that if you only have solutions which are compatible with that kind of choice,
Uh-huh.
in other words, if the fiducial, for instance, let me give you another example. If the fiducial metric was, we didn't choose it like that, but suppose it was only X dependent, then homogeneous and isotropic solution were impossible to achieve.
Okay.
You see what I mean? So we tried to introduce this breaking in as light as, in as softly as possible. But
Okay.
another thing that I wanted to add is that when you have, for instance, your perturbations, you cannot fix any gauge because the fiducial method already fixed.
Okay.
So you had to introduce all the scalars, for instance, the lapse perturbation, the shift perturbation, the diagonal term, the non-diagonal term of the trimetric, and that's only for the scalars.
Mm-hmm.
So I mean, because if you use this unitary gauge form,
Uh-huh.
that is now the gauge is fixed once for all. Of course, if you use the covariant form in terms of superfield, then of course you can reintroduce your gauge invariance.
Okay.
Okay.
I get some points. Okay, thank you.
Okay. Thank you. And thank you very much, Antonio, for reminding me about massive gravity. And then, okay.
That's true, actually. Actually, Pete, if I can say, at that time when we introduced, and probably when we discussed also, when you discuss also the theory, at that time probably people were mostly interested in this self-accelerating branch. But
yeah.
nowadays, with this DAISY result, this normal branch with the non-trivial dynamics may be interesting to see.
So in this case, as you answer, Campi, maybe it's not good for consider the black hole solution of this theory, right?
No, how can I say? The black holes for the theories are going to be very complicated.
So in that
Because
case, you have to find the covariant one first, or
maybe that's a possibility. Yeah, that's a good point. Or one has to find a good way to make sure that you solve all the constraints, because the constraints needs always to be solved. And then, so it's non-trivial step, that one. Yes, black holes is going to be, not a trivial solution to find. But it doesn't mean it doesn't exist.
okay,
Maybe it doesn't exist, but we don't know exactly what it is.
yeah, yes. I think it's good opportunity for me to come back massive gravity again to find some solution.
Yeah, for some case like self-accelerating branch, if I remember well, Schwarzschild black holes, but in PG coordinates is a solution.
Oh, okay.
But we don't know the correspondent Kerr black holes.
Okay.
So some
Okay.
solution are known for in PG coordinates it works.
Okay. Any more questions about it? If no more question, we have about maybe 15-minute break, and then we come back at about 3:45. Is this okay for you? Okay.
Yes,
Okay.
that's fine.
Let's take a break.
Thank you very much.
Thank you.
Before tutorial. Hello, hello, Antonio.
Yes,
Okay,
thank you.
yeah, I will try to call student. Bank is coming. Okay, yeah, I think it's time. So yeah, this is the last lecture, right? Yeah, so you have about 1 hour. Yeah.
Okay.
Okay, please start.
Thank you, Sir Chuck, for the. It was also nice to talk to you and to see you there. Okay, I'm going to start this this last lecture, probably talking about the simplest model that we discussed so far. I think probably is the simplest. So then, being the last lecture should be not too heavy. I hope so. Okay, I'm gonna give an introduction to this minimally modified gravity, theoretical formulation of BCDM, reconstruction, perturbation, comparative cosmology, and we're gonna talk a bit about this Maple workshop, universal workflows. So why minimally modified gravity? It's not clear. Main extension, generativity, add scalar vector or massive spin to polarization. So we should be open to all this possibility. In my research, I work mostly with scalar tensor theories and this minimally modified gravity. I find them both interesting because it seems to be a nice tool to probe gravity at different scales, cosmological scales, solar system scales, even class scales. Now possibilities are quite a lot to study these theories in the light of new upcoming data, both in terms of galaxy surveys and I should say CMB, BAO, and gravitational waves. So all this has to do with gravity, whether we like it or not. And therefore, to understand what gravity is means to go over these observables and try to understand as much as we can out of them. But in any case, extra gravitational modes are common, but they are not logically required. It doesn't have to, but of course it's a very interesting possibility. Minimally modified gravity changes the dynamics while retaining the two local gravitational modes of generativity. Why is this? Because if I can be honest, if I had to be honest with you, if we look into constraints coming from solar system, we don't see any modification appearing. So no fifth force in particular. But also at the level of clustering, yeah, maybe there is weak gravity, maybe not, because it's not so clear what we have. In the next few years, we will know much more about it. But it's quite possible that if there is a difference and the difference is tiny, maybe data needs to be improved. But they may find also good, in terms of G-effective, good agreement with generativity. they may. So we had to be ready to understand how gravity works. And of course, they had to also do double check what is this BO message we got from the data. If it's really energy, dark energy is dynamic or not. In any case, the central two is a modified nonlinear constraint structure. A degree of freedom count fixes the dimension of physical phase space, not the Hamiltonian on it. Altering constraints can modify the background and perturbation equations without activating a scalar gravity. After all, we saw in MTMG, minimal mass gravity, that even you don't have scalar degrees of freedom, the dynamics of the growth structure would be different in general if you are in the normal branch. That behavior can be strongly constrained in the future. Now, the nonlinear Hamiltonian count must be established before specializing to fit the method of its work. Of course, because if we do otherwise, it could be very dangerous. We would say, oh, this theory has only 2 degrees of freedom, but maybe it's strongly coupled. So first we had to do this nonlinear Hamiltonian count. So BCDM is a particularly simple realization of this idea, one of the simplest. I should mention Cascaton, but Cascaton in a way is also a bit more complicated. BCDM is not a vector tensor or generalized product theory. Its name reflects the promotion of the constant lambda in lambda CDM to a function v of phi. The scalar phi is auxiliary and supplies no independent scalar initial data. But because we see phi is not, does not have the same role as it had in DHOST or U-DHOST. Remember that in U-DHOST and DHOST, phi had to be strictly time-like, especially in U-DHOST, time-like. So the scalar phi is auxiliary and supplies no independent scalar initial data. The gravitational sector retains 2 tensor modes, while V of phi controls cosmological evolution. In particular, you don't see V of time, you see V of phi. And therefore, phi is not a Stuckeberg trick either, Stuckeberg field either. So how did we, this was a paper in collaboration with Shinji Mukoyama and a student, Doll. Start from the ADM Hamiltonian of general relativity. So we start from general relativity and we go to an ADM Hamiltonian. This is the simplest thing that we can do. And then we perform a canonical transformation. So a canonical transformation in the Hamiltonian system is just a change of variables. Introduce a cosmological constant in the transform frame and add the constraint needed to prevent the scalar gravity. So let me put it this way. Suppose I start from GR. I do a canonical transformation. Now I add a cosmological constant in the new frame. The theory is not anymore GR. because if it would be GR, it would be the transform according to the canonical transformation, but I added an extra bit. So this theory with the extra bit is not anymore generativity. And adding this, in general, adds a scale degrees of freedom. So we also add, so when we add this object here, we had to add a constraint to remove this extra degrees of freedom. We transform, so we have now a theory which has GR, transform GR, added a cosmological constant term in the new frame, which makes the theory not GR anymore, but breaks the constraint structure. So we lose one constraint, one first class becomes second class. So we had to add a constraint to make things work again, so that the degrees of freedom are only 2. After this, we transform with the inverse canonical transformation in the original frame. What we get is not GR, it's going to be a new theory. And because we have freedom in choosing this canonical transformation, this freedom leads to a general function V of phi. Now, in general, this minimally modified gravity are theories with the same 2 local gravitational degrees of freedom as generativity, but with different dynamics in general. Type 1 theories. Okay, we decided to classify them into types. Type 1, they possess an Einstein frame. So what it means that we can do a conformal transformation, for instance, so that the gravitational Hamiltonian can be transformed into that of GR, but modification reside in the matter coupling. And then type 2 theories. Those theories do not possess such a frame. So it's impossible to shift all the changes in the gravity sector to the matter sector, keeping GR as generativity. The theory that I'm going to discuss, which is very simple, is going to be a type 2 theory. Okay. All right. So this was, I'm going to give you here the algorithm to construct the CDM, although I'm going to mostly skip it and tell you the final result. So, okay, we start from the ADM Hamiltonian generativity. We perform a canonical transformation to the variables n and I gamma aj, and the cosmological constant in that transform, add the cosmological constant in that transform frame. Add the gauge fixing constraint so that no scalar gravity is activated, transform back to the original ADM variables, couple ordinary matter minimally in the original frame. Okay. The cosmological constant introduced in step 3 becomes a potential V of phi of an auxiliary field after the inverse transformation. If this is not clear, which probably it should be, after these steps, we are going, I'm going to write to you the Hamiltonian of this theory. Now, how does it look, this object? Notice that in this theory, we have written the theory in terms of ADM, which means we are in a preferred frame. So which means that we can reconstruct the covariant theory adding at least one scalar. That scalar it's not one of the scalars you see here, because otherwise those objects will be time. So there should be an extra scalar. As always, when you have ADM, we should add new fields on top of the fields that you see in ADM. In particular, we see that one part is proportional to the lapse times this H naught GR, which means GR is the same expression as in generativity, plus NI HIGR. This is the momentum constraint as in generativity. And then let's see this Hamilton. So N and Ni don't appear anywhere else. So we can consider them to be purely Lagrange multipliers. So the set for constraints. Then we have a bunch of Lagrange multipliers. One is this lambda c, and lambda c sets phi to be proportional to the trace of pi. We have another Lagrange multiplier which sets the momentum conjugate to phi to be 0. We have a third, this is a vector, but what it really means, this is the scalar part, because if you do integration by parts, this will be nabla I, lambda I, and essentially this picks the scalar part. So this is the scalar part of the gradient of phi, or if you want, it's nabla square phi. So nabla square phi must vanish. And finally, the term here is multiplied by n. So n actually has this object plus this. Now you can see immediately that the Hamiltonian constraint changes from generativity because we add to H naught GR, which is the expression in generativity, a term which is proportional to the potential phi. And immediately you see that this constraint will not commute. So its Poisson bracket will not be 0 with pi phi. So the Hamiltonian constraint stops being a first-class constraint because it doesn't commute with all other constraints. And so what it means is we have lost diffeomorphism. But this is true because we are in ADM formalism. So in principle, we would need to reintroduce time in a different shape. And that field, which is time-like, is not phi in general. Because the constraint on phi just says that the Laplacian on any background of phi is equal to 0. This configuration allows the solution phi to be constant. And phi to be constant definitely is not a time-like vector. But notice this will not be a breaking of the foliation because the field which makes the foliation is not phi, but it's another field. Okay. So we have 1, 2, the scalar part 3, 4, and then 3 constraints from Ni. It's interesting because everything else does not break 3D diffeo. So we should expect 3D diffeo to be a symmetry of the theory. And in fact, if we consider the extended momentum constraint, including the contribution from pi, then we can find that that object is a first-class constraint. So Hi will form 3 first-class constraints. Okay. Now, the key idea, the symbol V in VCDM emphasizes that the function V of phi replaces the constant vacuum term of lambda CDM, while the gravitational sector still has exactly two local tensor modes. The auxiliary field changes the constrained surface, not the dimension of the physical phase space. Okay. I mean,
Sorry, can we say phi is the extra DOF of the massive particle?
no. Well, okay. By massive particle, what do you mean? The graviton?
The graviton, yeah.
Okay,
But
no, yes. Okay, so then I got your point. Okay, in this theory, actually, the graviton will not be modified. So what it means, the graviton will remain massless.
So at first your theory was massive, and then as I realized you separate the extra mode and somehow appears in the scalar field in a new.
No. Okay, I'm sorry. The theory I discussed last lecture is a completely different theory. You had to forgive me. I mean, I didn't. So this is a completely different theory. Another construction, if you want, of minimal theories, much simpler. And in particular, we don't care anymore of a massive graviton. We will not have a massive graviton. But we will probably realize one of the simplest minimal theories that one can build. But no, it doesn't have any connection with the theory I discussed before of the minimal theory of massive gravity. In particular, phi will not be, all these constraints, as you notice, are constraints which do not affect the tensor structure because are constraints on trace, scalar part. So the tensor mode in this theory will be exactly the same as in GR. In other words, in this theory, there is no external field, but there is a Stuckeberg field, which has been said to be equal to time. And all the fields are here except this Stuckeberg fields, which has been, which is time-like. So this theory has U-DHOST, for instance, also has minimal theory of massive gravity. You notice that all these constrained theories, most of them have time-like scalars inside. And this is one of them. But yeah, this is a bit different.
Antonio, I have one question. I know some theory that they call like running vacuum, that they set cosmological constant to be function of Hubble. So is this a subclass of your theory or not?
What's the name of the theory, by the way?
It's like running vacuum model. It's like this chain lambda to be lambda plus like some constant multiplied by Hubble square. So like,
okay.
Yeah.
Now, okay, I honestly, I don't know much that theory. Now you tell me, but maybe it's different. Although, okay. So okay, let me put it this way. Maybe it's possible to embed the theory in this theory, but not necessarily they are the same thing. I'm going to tell you. Okay, so if I understand that theory implies something about this effective cosmological constant, which is actually functional of something. And then that thing can be mimicked inside this theory. but the way that it's constructed may be different, and they may be different at the level of maybe same at the level of background, but different in terms of perturbation. But I will try to learn a bit more about that theory. Thank you very much.
Yeah, I see. Thank you. Yeah.
Okay. Now, because we have the Hamiltonian, it's very simple to find the Lagrangian by doing a canonical transformation. Now, interesting point is because lambda was setting a constraint on the trace of the momenta. When you find the Lagrangian, the Legendre transformation, gamma dot and pi will have some gamma, some lambda, and lambda will enter non-trivially, giving this quadratic term. This constraint remains the same, and we have, as you notice, we have the standard term in Einstein-Hilbert plus this V of phi. Now, V of phi, because this object sets phi to be constant or function of time, this V of phi can be constant or a function of time. That depends on the general solution. Sorry. So for V of phi equal to 0, sorry, this should be V comma phi phi equal to 0. It reduces to general relativity. Of course, you may, okay, if V of phi is equal to 0, of course, V is a constant, and this quantity will behave as a cosmological constant. But for V of phi different from 0, the preferred slicing remains. But we will see that this is true, but not all, how can I say? It's true, but this is not the only possibility for the theory to give general relativity, as we will see later on. Okay, so let's see how many degrees of freedom I have actually. So we have gamma aj with the pair pi aj. So this is 6, 12, and then I have phi and pi phi adding to 14 phase space variables. If we go to the original Hamiltonian, so we have 14 phase variables, n and I are not counted because they are just a Lagrange multiplier, they enter linear. And then we have 3 first class, 1 second class, 2 second class, 3 first class, 4 second class. So 1, 2, 3, 4 second class, and 3 first class. First class, there are 3 extending momentum constraint, special diffeomorphism holds. And second class, 4 independent constraints, Hamiltonian type, P phi, trace momentum relation, and scalar part of di phi equal to 0. If you want, this is Laplacian of phi equal to 0. Okay, then we have 1/2, 14, minus 2 times 3, minus 4. This 6, 4, and 10. 14 minus 10 is 4 divided by 2, 2 degrees of freedom. Can we modify this? Well, yeah, of course. Modifying this theory is pretty simple because, for instance, we can change how these constraints look like. So this theory can be easily modified, actually. But let's keep it this one as a very simple example. And notice that this degrees of freedom this theory has a free function, which is the potential V of phi. Now, let's consider the theory on a Friedel-Lemaitre Robinson-Walker ansatz. So n is a function of time, the lapse is 0, gamma ij is proportional to identity at the flat case, and H is the standard Hubble factor. The mini superspace Lagrangian for comoving volume is an A cubed n plus square minus 3H squared. That's standard is in general relativity minus V of phi. This is the non-trivial part. Notice that because we have to assume homogeneous and isotropy, phi in general is a function of time. Therefore, the constraint nabla square of phi automatically goes to 0 on the background. We have minus 3/4 lambda square minus lambda 3H plus phi. This is corresponding to the trace of the extrinsic curvature, plus the Lagrangian matter if we have a fluid. So the gauge fixing term vanishing on the homogeneous answer. So we have this object here. So we can vary with respect to different fields. But in lambda, we take that lambda is negative 2H minus 2/3 phi. The Laps equation n is going to give you the whole thing here, actually. But we had to replace lambda inside this relation. And what we are left is phi square is 3v plus 0 over mass Planck square. So the Laps equation by eyes look quite different from standard Friedmann equation, but we will see in a second what does it mean. And then we have the scalar field phi, and we take the variation with respect to scalar field phi. We get phi is equal to 3/2 v comma phi minus 3h. And then you see, interesting enough, this equation is only equation of phi and h. This equation determines what is lambda. And what about this? Of course, on top of this, we also have the continuity equation for dust, because dust Lagrangian is the same. So the equation of motion for the fluid is the same. Rho here is the sum over all matter fields, standard matter fields. But you notice I have phi square. Phi can be deduced over here. If I replace it here, I will have an h squared equation, which looks very much the standard Friedmann equation. Okay, what can I do here? For instance, I can take the time derivative of this equation here, and the continuity equation will tell that phi dot over n is 3/2 rho plus p over mass Planck square. Now, this is an interesting relation because rho plus p is the sum over all the matter species. So in this row, there is a contribution of dust, there is a contribution of baryon, radiation, but not the cosmological constant. And P, the same, is the total pressure. Baryon, dust, radiation, neutrino, if we have. And rho plus P for standard matter is positive. Therefore, phi dot over n, phi dot is positive. Phi dot grows always. And that's very nice, because what it means that we can invert time with phi. In a similar way, we can actually deduce what is the second Einstein equation, taking derivatives, get the h dot over n, and you notice this rho plus p, and then we have this interesting object, 3v comma phi phi, second derivative with respect to phi, and phi is time of, can be deduced by this, by integrating up to an initial condition for phi. But it's interesting, when v comma phi phi goes to 0, this becomes exactly GR. This becomes the second Einstein equation in generativity, when v comma phi phi equal to 0. When v comma phi phi different from 0, then this object will be modified. Minimal matter coupling yields this object here. So for v comma phi phi equal to 0, this reduces to general relativity result. H over n is minus rho plus p divided by 2 mass Planck square. Now, as I said, we can combine the Laps function and the phi equations, yielding the familiar Friedman form. 3 mass Planck square h square is equal to rho, which is the standard rho for the matter fields, plus rho phi, and rho phi is this object here. Now, why do I say that when v comma phi phi equal to 0 is lambda CDM? Because when v comma phi is equal to 0 means that v phi is constant. So this last term becomes a constant. Now, when v phi is constant, v will be that constant times phi plus another constant in general. But when I multiply v minus phi comma v comma phi, what is left here is a constant. The linear term in phi goes away. So whenever v comma phi phi is 0, rho phi becomes a cosmological constant. So that's the contribution in the Friedman equation. Again, when v comma phi phi is 0 in this equation, you will find that p phi is equal to minus rho phi, which is a cosmological constant. But otherwise, this object will not be. And because, all right, so v comma phi phi then determines the behavior of the solution. Now, background reconstruction. And this is important here. For any prescribed expanding Friedman, Lettermeter, Robinson Walker history, h of the Laps, h in terms of the e-fold variable, with the e-fold variable is equal to log of a over a naught, and ordinary matter history, one can reconstruct a local BCDM potential. So what do I mean by this? So if I change variables, so you see in this relation here, t was a general t variable, and n was the lapse associated to t. But if I impose that, if instead of t, I use the log of a over a initial, which is my e-fold variable, then the equation can be solved into this way. Of course, I am using this variable assumes that h is different from 0 during the history of the evolution. And rho plus p, so if in an expanding universe h is positive, rho plus p for standard math is positive, we can solve, and we can also invert n in terms of phi. Okay, there is this free initial condition, phi naught at some value of the e-fold and naught. Apart from that, this is given rho and p. But do we know rho and p? Yes, we do, because rho and p satisfy the standard continuity equations. So, for instance, rho of dust goes like inverse of a cubed. Rho of radiation goes inverse of a to the fourth. And the pressure for radiation is 1/3 rho, and for dust is equal to 0. So I know exactly how those objects depend on the e-fold variable, or if you want, how depend on A. Except I don't know this H. But now comes an interesting point. Suppose that rho is known as a function of the e-fold because it's the sum over all matter species. Rho phi is this object here. Okay. Let me give it, and this maybe goes back to the question of Sirachak. Let me suppose rho phi to be a given function of the e-fold. Can be, I don't know, rho phi to be some function, blah, blah. It can be, but it can be a function of even h, whatever. So it must be a given function of the e-fold. Then, if it is a given function of the e-fold, rho is known in terms of e-fold. E-fold means essentially a, no? Because n is equal to exponential of a. So if I know rho and rho phi in terms of a, I know how they behave in terms of the e-fold. But what it means is this Friedman equation sets h squared as a given function of e-fold. Okay? Question is, can I reconstruct the potential, which gives me the kind of... so when I reconstruct the potential, I reconstruct the theory, because the theory is fixed after we give the potential. After we give the potential, the theory is fixed up at most to this initial condition phi at some given e-fold. So phi is phi naught plus this object. And then h of n is given. So I can solve this equation analytically if possible, but numerically is also fine, to find what is phi as a function of n. So this is just an integral. I don't have even to solve a differential equation. But because phi d phi over dn is positive, monotonicity permits inversion to find the e-fold in terms of phi. However, the potential then is obtained analytically, if we know n analytically as a function of phi, because this was the Laplace equation. V was 1/3 of phi squared minus rho of n, but inverting, I will know what is rho as a function of phi. And after, I will know what is V as a function of phi. So reconstruction, so we reconstructed, and that's nice. However, we should say that reconstruction is not yet a stable model. One must test invertibility, regularity of V of phi, scalar perturbation, and the range of validity of the preferred foliation. And the last thing is the most important, the range of validity of the preferred foliation. The foliation which allowed us to write the theory in ADM form, which means the Stokes field must always be time-like. Stokes field is not phi, it's an extra field. If the target is history of basic generativity with a cosmological constant, that's very simple, then phi is equal to C minus 3H, substitution is a linear potential, okay. And as you can see, V comma phi will be 0. Although the potential is linear, the effective energy density, rho phi, is purely a cosmological constant. Now, what happens to the tensor modes? And I'm going back to one of the first questions I got for this lecture. The tensor action is exactly that of generativity. If I study the tensor modes, and because all the constraints we have do not affect the tensor structure, so it's no big surprise that my tensor mode is exactly as in generativity. In particular, the speed of propagation of the tensor mode is exactly equal to 1. And it doesn't have any mass. However, given that is true, we should notice that A here is a scale factor. So what it means is that the propagation equation is standard, yes, but H is not the same H of lambda CDM because it has, in general, a dynamical component. So the friction term and also A as a function of time will change. But in practice, the speed of propagation, we can say, constraints from that will not be affected. So no gravity on mass, the speed of light, CT squared is equal to 1. And And then standard friction gravitational waves are damped solely by the cosmic expansion. Okay, now scalar perturbations. If we look at the scalar perturbation, in the scalar sector, the only propagating modes are those supplied by matter. By construction, this is another minimal theory, so they don't introduce scalar degrees of freedom. So DHOST, U-DHOST, Ondensky introduce scalar degrees of freedom. This doesn't. And I find it fascinating what really gravity is, but we may need to know, we may need to wait a bit more time to understand better. Anyhow, so in the scalar sector, the only propagating modes are those supplied by matter. For one barotropic perfect fluid, the high K-sound speed and no-ghost condition are the GR ones. So if I look into sub-horizon regime, I don't see any difference. And this makes sense because, yeah, the matter Lagrange are still the same as in general relativity. So the matter equation of motion are the same. What changes is this behavior at large scale produced by this function p of phi, and phi is time dependent. The display no-ghost inequality assume rho plus p positive, gradient stability addition requires c squared positive, but this is standard as in general relativity. For dust, integrating all auxiliary perturbation, like we did for minimal material massive gravity, we will have, you notice that this is not exact, this kinetic term is not exactly the same in general relativity. In general relativity, this object will be zero, this quantity will simplify, and this simplifies a lot. But in the sub-horizon scale, when I study clustering at short scales, then the k square will dominate, and then you see that this ratio will still go to 1. So at sub-horizon scale, the modification is suppressed and GR is recovered locally. Okay, let's go into summarize of these lectures. So I discussed 4 theories, 2 mechanisms. The DHOST, the defining mechanism is covariant kinetic degeneracy. And the local gravity modes were 2 tensor plus 1 scalar. In the U-DHOST, degeneracy on scalar foliation. Degeneracy meant a degeneracy constraint on some functions. And this I had 2 tensor plus 1 scalar plus 1 elliptical mode. And TMG, 2 added the second class constraints. Now we put constraints at the level of the Lagrange through Lagrange multipliers. That's the second mechanism. And we had 2 tensor mode, which are massive. And then we deconstructed a canonical construction plus gauge fixing, which was given BCDM, which has 2T, so 2 tensor mode, but massless. This NTMG and BCDM have no gravitational scalar at all, and a scalar cosmological mode comes entirely from matter. And of course, each one of them has its own different phenomenology. Of course, there are other possibilities, but I think in terms of phenomenology, I think this is quite an interesting set of theories which can study different phenomenology for in gravity. Okay, constraint flow view. So first, we had to think about the candidate modified action, have in mind what we want to constrain, what we want to remove. We can choose the side of DHOST U-DHOST. In this case, we need a singular kinetic map. So the kinetic matrix must be degenerate. This would give us a non-zero eigenvalue, non-zero eigenvector for a zero eigenvalue, which then defines a primary null constraint. And the time derivative of this will introduce a secondary constraint. And the two of them will remove the extra degrees of freedom, which would be orthogonal otherwise. Or we can take a different road. We add constraints at the level of the Lagrangian by means of Lagrangian multipliers. We had to check all the Poisson algebra to understand the number of first class, the number of second class. But also in this case, in the end, we want to reduce the phase space. Both had to be tested against extra stability tests. The fact that we remove degrees of freedom does not necessarily mean we remove all possible instabilities from the models. This must be checked. Okay, the goal of the workshop, well, maybe the goal of these lectures I should have written. So the final lecture turns conceptual distinction into a working calculation protocol. This is aimed for students who maybe are interested to look into the physics of constrained system. Goal, we should not ask a computer algebra system to find the physics. The real goal, make the computer verify a sequence of physics decisions whose meaning is already understood and are in our mind. We should start with some kind of picture of what we want from a theory. And then, yes, use computer algebra to implement. Let me study maybe a universal background workflow. It's pretty standard. For any ADM action, adopt the ansatz. N is the level of background, of course. N is a function of time. The shift is 0. And Hij is proportional to identity through the scale factor square. Keeps the lapse arbitrary and define H, the Hubble factor, to be A dot over NA. Keeping the lapse arbitrary helps to double check the equations, but it's not necessary. Keep the homogeneous fluid of shell with a Schutz-Sorkin action. This is a very interesting advice I give it to students. When you study perfect fluid, use the Schutz-Sorkin action, which is very neat and clean and easily adoptable in all background environment that I know. And in particular on this on this homogeneous and isotropic background, it consists in mini superspace as C minus. This is square root of minus g that in ADM becomes NA cubed. And we have a rho of n plus n over capital N L dot. Now, capital N is the lapse, is a scale factor, so far so good. Little n is a scalar, which will correspond to number density. And L dot is another scalar, which sets a constraint. Again, this is another constraint object. Indeed, when you find the equation of motion for L, this is L dot, so we had to integrate by parts, and the equation of motion that L sets is that A cubed n is a constant, which means that little n is a constant divided by A cubed. That's exact number density of a fluid. Vice versa, when I find the equation motion of this action with respect to n, I will have L dot a cubed with a negative sign minus n a cubed rho comma n. A cube simplifies, and you get L dot minus n is equal to minus n rho comma n. And in this fluid approach, the pressure and rho are linked through this n rho comma n minus rho. Okay, so the rho comma n is nothing but p plus rho divided by the number density. On this equation, the metric variation becomes, you can actually show that using this equation, you can find this. But you don't need to. You can just keep it this one all over the place. And yeah. The action and the compact response formula are two levels of the same description. Oops. And okay, substitute the homogeneous answers into the action, but do not set n equal to 1. Remove only genuine total derivatives, record discarded boundary terms, vary NA, whole homogeneous field, including L in this fluid action, and N, and every multiplier. Solve multiplier constraints first, substitute them into the remaining equation, verify the another identity. Only now set n equal to 1 or change to if all time. Anyhow, so this is for a complete background calculation, supplement the algebraic residual in script with these checks. The GR or lower theory limit. The matter continuity identity, one background equation must follow from the others. So that's a fundamental check that not all background equations are independent. This is also what so this is a standard check must be always done. Dimension homogeneity of every Friedman term, okay, units and so forth and so on. I think I have, okay. So universal scalar perturbation workflow. In my convention, I define the perturbations for the scalar modes into this form. I have a perturbation for the lapse, perturbation for the shift, zeta perturbation for the diagonal part, and the non-diagonal part into this capital field A. The unitary gauge implies E equal to 0, and delta phi, if you have a scalar field, equal to 0. But other gauge can be chosen, in particular, Newtonian gauge, for which E equal to 0 and chi equal to 0. Keep bookkeeping parameter epsilon here, so that you can expand the action background equation to find the mini superspace. The action first order in perturbation must vanish on the background equations. This is a strong test of sign and integration by parts and test of the background equations. And the second order contains constraints and physical kinetic gradient matrices. The correct elimination order, quadratic level, separate fields into three groups. The gauge variables, the one that can be fixed. And after the gauge is completely fixed and admissible, that gauge choice, you cannot do anything else. So unitary gauge versus Newtonian gauge, but you cannot take both at the same time. Auxiliary variables vary first and solve their constraint equation. Dynamical variables compute the reduced kinetic matrix only after all auxiliary fields have been eliminated. Okay, apart from this detailed CDX files and throughout U-DHOST, okay, I think, yeah, you will find that in Maplefy, I arrive at the equation motion by implementing my own procedure, but also using functional derivative inside the physics package of Maple. Okay. When you use Maple, be careful about simplify, especially, or expand, because they, if you have a very complicated expression, they may slow down a lot your code. Okay. So we are almost at the end of it. Okay, these are just checks. What is important actually, after you check that your background equations are correct, the gauge fixing was acceptable and done properly, you had to solve for the constraints, yet then to guess the number, a differential type of auxiliary equation. So this is, for example, very important in U-DHOST, in DHOST too. And then after you found the object which are purely Lagrange multiplier, which means without dynamics in this sense, then you reduce the action. You remove all auxiliary solution back into the equation agrees with varying the reduced action and solving algebraically, okay, for the variables. Then study UV limit. You go into the high K kinetic and gradient matrices to produce known limits. In this sense, you find the no-ghost condition and the speed of propagation. The theory limit, those also study theory limit when dose goes to Ondensky or GR, when U dose goes to Z equal to 0, you see the M V55 equal to 0 and TMG when M equal to 0. So you should always try to go to known limits to see what happens. Independent root, reproduce one key equations by a second method. Example given, ADM versus covariant expansion, Hamiltonian formalism. I gave Maple files for DHOST, U-DHOST, MTMG, and VCTM. And the most elaborated one is U-DHOST, where I found also the no-ghost condition and the speed of propagation, at least for one branch. Okay, let me conclude. I went 2 minutes over time, I think. VCDM is a type 2 minimally modified gravity theory with 2 local gravitational tensor modes and no scalar graviton. The tensor sector VCDM behaves exactly as general relativity. A Maple workflow formalizing constraint, elimination of order, and stability checks is crucial. A rigorous verification ladder prevents computer algebra errors. Thank you very much.
Okay, so is there any questions?
Thank you for your nice talk and presentation. My question is that can we obtain your three-dimensional Lagrangian from the four-dimensional diff invariant by spherical reduction?
Spherical reduction, what does it mean? Sorry, I don't know.
It's something like a Kaluza-Klein reduction because your scalar field does not have a dynamic. It's something like a dilaton field. Am I right?
Okay, you raise an interesting point. I don't know exactly the answer to that, but what I would do to check, to explore what you say, is first to transform the theory into a covariant theory, which means reintroduce the Stuckelberg field. Now, once you have the Stuckelberg field, your Lagrangian will be covariant, given the fact that one of the scalar fields, though, is always time-like, okay, because you have typically square root of minus kinetic term. And but apart from that, yes, I think it's after that, I think it's possible to investigate what you are saying. Okay. It would be interesting to see whether they have some some UV. I don't know how to say it. Some UV limit. I had to say that some people studied in the case of the Cascaton, some people studied theories with vector fields, time-like vector fields.
Well, yes.
So that is also a possible interesting route, but yeah, it's not 100%. It's not easy to prove complete equivalence among theories. One has to do theory definition or conformal transformation, something like that. It's a very interesting topic, but I don't know much about that.
Yeah. Thank you. Thank you for your patience and my question.
No, thank you.
Is there any more questions? So I think no, but it seems we have one online. Yeah.
Oh.
Yeah, what's that?
I mostly use Mathematics. Is there a way to run a complex Maple code in Mathematics, or would I need to recreate the code myself based on your Maple code? Good point. It's not easy because Mathematica, you had to have external packages, GR tensor, exact, and then you have somehow there is no easy way to convert. But of course you can convert by hand because those packages have similar functions. Okay. So there is no easy dictionary, but it's not difficult either. If you have the chance to get Maple somehow, then maybe it's also interesting to try it out.
Okay, I think it's only one. Is this? That's all. And okay, so please thank the speaker again. Yes.
Thank you very much.
Yeah.
I hope I come to visit soon.
อะไรนะต้องถ่ายรูปหมู่กับพิยากร
Oh, also, wait, Antonio. Compi said that we have to take group photo with Antonio, right? So yeah, again, so the student and audience, please come to the front row and then take photo with the Antonio.
Okay, thank you very
Yeah,
much.
just a few minutes. Yeah, I know that it's almost 7 p.m. in Japan. Yeah.ได้ไหมครับทางนี้ไหมครับทางนี้ครับ Okay, thank you, Antonio. Thank you very much. Yeah.
Thank you very much.
Yeah.
See you in Thailand or
Yeah.
anywhere.
Yeah, sure. Yeah. It's time for dinner, right? For you, right? Yeah. Bye.
Bye.
And for us, it seems next is the dinner, and I think it should be the same place, right? And after that is tutorial start at 6:30. So yeah, tutorial 6:30. I don't know, but yeah, maybe let's meet again in this room again 6:30. Yeah.